Hello. 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 Am I
Hello,
audible
am
to
I
you all of
audible
you?
to you all of you?
Yes, ma'am.
Okay. Okay.
Okay, okay.
I think
I
we
think
can
we can
start now.
start now.
So, hello
So, hello
everyone. So, I
everyone.
am
So, I
Parul
am Parul
from IT
from
Bombay,
IT
and
Bombay,
today we are
and today
starting
we are
the
starting the
subject physics of
subject physics of
nanomaterials,
nanomaterials,
and this is
and
week
this
one
is
of
week
this
one of
lecture.
this lecture.
So,
So,
sorry, I think
sorry,
it's
I think it's net.
yeah.
Yeah.
So,
So,
this lecture
this
has
lecture
the
has
objective.
the
So, first of
objective. So,
all,
first of
we
all,
will
we will
see like what is
see like
the
what is
as
the
the
as the
name suggests
name suggests
that physics of
that physics of
nanomaterials.
nanomaterials.
So,
So,
nano
nano,
the what is the
the what is the
properties
properties
changes when
changes
we
when
move
the
from
we
the
move
bulk to
from the
the
bulk to the
nanomaterials. So
nanomaterials.
first we will
So
define
first we will define
nanoscale.
the
What does it
nanoscale. What does
actually
it
mean?
actually mean?
Then we
Then
will see
we
that
will see
how
that
the
how the
reactions or
reactions or
chemistry, optical
chemistry,
properties,
optical
mechanical
properties,
property
mechanical
changes
property changes
when we move on
when we
from
move
the
on
bulk to the
from the bulk to
nanoscale.
the
So
nanoscale.
how the
So how the
surface
surface
thermodynamics changes.
thermodynamics changes.
Second thing is the
Second
very
thing is the
interesting
very
part of
interesting
this
part of this
nanomaterials is
nanomaterials is
like we are
like
moving
we are
from the
moving from
classical
the
to the
classical to
quantum
the
regime.
quantum regime.
So we will see
So
like
we will
how
see
the
like how
energies
the energies is
how the
the how
energy
the
levels are
energy levels are
quantized, what is
quantized,
the shifting
what
of
is
the
the shifting
density
of
of
the
states,
density of
and we will
states, and
analyze
we will
the
analyze
quantum
the
confinement.
quantum confinement.
After that, there is
After that, there is
classification of
classification
the
of the
nanomaterials,
nanomaterials,
which is
which is
0D, 1D,
0D,
2D,
1D,
3D. So
2D, 3D.
basically,
So
that is
basically,
called the
that is called
structural
the
taxonomy.
structural
So we
taxonomy.
will
So we will
classify the
classify the
materials on the
materials
basis
on the
of
basis of
uh, the
uh,
si-
the
confinement of the
confinement of the
nanomaterials in the
nanomaterials in the
all the dimensions.
all the dimensions.
The next is
The
we will see
next
the
is we will see the
applications of the
applications of the
nanomaterials.
nanomaterials.
So in
So
the
in the
medicine, energy
medicine, energy
storage,
storage,
and the computing
and the computing
architecture.
architecture.
So
So
right now, like I
right
want
now,
to
like I want to
share one interesting
share one
part in
interesting
this.
part in this. So
Uh,
uh,
I am working in the
I am working in the
photonics lab,
photonics
and which
lab,
is
and which is
in our lab
in our lab
we are making
we are making
fabricating the chips,
fabricating the
in
chips,
which we are
in
doing
which we are doing
also
also
like
like
waveguides,
waveguides,
resonators on an
resonators on an.
obviously since I'm
Obviously,
telling the
since I'm
chip,
telling
we are
the chip,
using
we are
all
using
the
all the
fabrication materials which
fabrication
we
materials
study
which we
later in
study
this
later in
course like
this course,
SEM,
like SEM,
TEM,
TEM,
and what is the
and what is
lithography
the
techniques,
lithography
all these
techniques,
things, like
all these
how
things, like how
can we
can we
fabricate all these
fabricate
nano
all these
devices.
nano
So
devices.
for that
So for
also we
that
will
also we
see
will
into this
see into
lecture.
this lecture.
So
So
first of all,
first of all,
so when
so when
earlier the
earlier
past
the
is we
past
have
is we
the
have the
dimensions from 1
dimensions from 1
micrometer to
micrometer
1
to
mm.
1 mm.
So the size
So
is
the
very
size is
large.
very large.
Initially, like
Initially, like
uh,
uh,
we were dealing
we
with
were dealing
that
with
size of
that size of
devices.
devices.
After that,
After that,
we
we
the
and
operating
the
speed is
operating
also
speed
from
is also from
kilohertz to
kilohertz
gigahertz.
to gigahertz.
Then we move to
Then we
the
move to the
then the classical
then the
optics
classical
is
optics
dealing
is
in
dealing
this
with in
category. The
this
speed
category.
is
The
fast,
speed is
but
fast,
still the
but still
dimensions
the dimensions
is in the range
is in
from
the
1
range from
micrometer to
1
1 mm.
micrometer to 1 mm.
Then came
Then came
semiconductor
semiconductor
electronics, where
electronics,
we
where
reduce
we
the
reduce
size,
the size,
but the speed
but
is
the speed
also
is
speed
also
is lesser.
speed is lesser.
Then there is one
Then there
term
is one
terms
term terms
nanophotonics, where
nanophotonics,
the
where the
dimensions are
dimensions
less
are
as
less
well as
as well as
the speed is
the
fast.
speed is
So
fast.
right now
So
we are
right now
dealing
we
with
are
these
dealing with
features.
these features.
We are
We
moving
are moving
from
from
electronics to the
electronics to
photonics,
the
where we are dealing
photonics,
with
where we
the
are
wide
dealing with the
band gap
wide band gap
materials. We are looking
materials.
for
We are
the
looking for the
quantum sources,
quantum sources,
detectors. We
detectors,
can do
where we
the
can do the
where we can use the
where we can
devices
use the
for the
devices
quantum
for the
imaging,
quantum
quantum
imaging, quantum
communication. So
communication.
now,
So now,
to make the
to make the
devices, how we
devices,
are
how we are
unlocking,
unlocking
what is the
what is
impact
the
of the
impact of the
nanotechnology. So we are
nanotechnology.
dealing
So
with the
we are dealing with the
nanomaterial
nanomaterial
devices,
devices,
and
and
so it is,
so it is,
when I'm saying
when
the
I'm
nano,
saying the nano,
so it
so
means
it means
it is
it
obviously
is
it's a
obviously it's
prefix
a
unit
prefix
which
unit
has the
which
dimensions
has the
of 10 raised
dimensions
to
of
power
10 raised to
minus
power
9
minus 9
meter.
meter.
So
So
this is
this is
nanomaterial science,
nanomaterial
and how
science,
are
and
we
how are
using,
we
like
using,
where
like where
uh, the
uh,
fields
the
where we are
fields
using
where
it,
we are
like
using
health
it,
and
like
medicine,
health
like
and medicine,
endoscopy
like
we are doing,
endoscopy we are
drug
doing,
delivery
drug
has the
delivery
particular
at the
location,
particular
we are
location,
using
we
such
are
things.
using such things.
Then next
Then
generation
next
electronic
generation
devices
electronic
that we are
devices
using
that we are using in
quantum communicating
quantum
telecom
communicating telecom
applications,
applications,
and like
and
1550
like 15
nanometer when
50
we are dealing
nanometer when
with,
we are
then we
dealing
talk
with,
about
then
the
we
next
talk about the
generation
next generation
electronics,
electronics.
and then
And then
lightweight
lightweight
materials,
materials,
and the
and the
elastic strength is
elastic
very
strength is
high
very
as
high
compared to
as
the bulk
compared to the
materials,
bulk materials.
and obviously
And
sustainable
obviously
energy
sustainable
sources we're
energy
moving
sources, we are moving
as we move from the
as we
bulk
move from
to
the bulk
low.
to low.
So
So, so
basically we are
basically we
defining
are
the
defining the
material, redefining the material
redefining the
world.
material
So
world.
what was the
So what was
classical
the
assumption?
classical
In
assumption?
classical
In
material
classical
science,
material
we were
science,
dealing with
we
the
were dealing with
intrinsic
the intrinsic
properties like
properties,
melting
like
point,
melting
color,
point, color,
conductivity, which were
conductivity, which
created
were
as a, treated as a
treated
constant.
as a constant.
So now
So
a
now
macro
a
block
macro
of
block
gold is
of
yellow.
gold is
But
yellow.
now when we
But now
will
when
deal
we
with
will
the
deal with the
nanoparticles of the
nanoparticles
gold
of the
or
gold,
any
or
metallic
any metallic part,
nanoparticle like gold,
nanoparticle like
silver,
gold,
copper,
silver, copper,
the color
the
changes.
color changes.
Why does this
Why
color
does this
changes? We
color
will
changes?
see
We will
like what
see like what
are the
are
properties
the
that is
properties
changing
that is
time to time.
changing time to time.
So when we're
So
talking
when
about
we're talking about
nanoscale, now the
nanoscale,
particle
now the
size will
particle
be in the
size will
range
be in
of
the range of
1 to 100
1 to
nanometer,
100
and
nanometer,
then
and then
we will
we
see
will see,
like at the
like
surface
at the
level
surface
how the
level,
van der Waals
how the
force
van
is
der Waals force
changing.
is changing.
So the
So the
nanomaterial
nanomaterial
is an
is an
entirely different
entirely
physical
different
regime.
physical regime.
So we will
So we
see
will
like
see
how the
like
properties
how
are
the
changing.
properties are
So
changing.
in
So in
lectures also,
lectures also,
uh,
uh,
so we have
so we have
it is defined
it is
what is
defined
mean by
what
the
is meant by the
nanomaterial. So
nanomaterial. So
first is nano,
first is
which
nano,
means
which
1
means
billion,
1
that is 10
billion,
raised to
that
the
is 10
minus
raised to
9
power minus
nanometer
9 nanometer
meter, sorry.
meter, sorry.
And what is
And
material
what is
which has
material which
definite
has
mass,
definite
volume, and
mass,
occupies
volume, and
space,
occupies
and we were
space,
dealing
and
with
we were
the
dealing with the
like
like
materials can
materials
exist in
can
different
exist
states:
in different
solid,
states:
liquid,
solid,
gas,
liquid,
and
gas,
plasma. So
and
when we are
plasma. So
dealing with
when we are dealing with
plasma,
plasma,
there are
there are
ions, and
ions,
the
and
ions,
the
which
ions,
ions?
which ions.
So
So
there are
there
several
are several
processes
processes
like
like
sputtering.
sputtering.
This is a
This is a
deposition
deposition
process
process
where
where
the
the
inert gas
inert gas
atoms
atoms
are used
are used
to create a
to
plasma
create
like
a plasma, like
argon,
argon,
helium.
helium.
So
So
there are some
there
physical
are some
processes
physical
which we will
processes
deal
which we will
in
deal
the
in the
further lectures,
further lectures,
and these are
and these
characterized
are
by the
characterized by
specific
the
physical and
specific
chemical
physical and
properties.
chemical properties.
So
So
now when we
now
will
when we
define
will
that it's a
define that it's a
nanomaterial or not,
nanomaterial or not,
so for
so
that
for that
we will say
we
that
will say
if the
that if
material
the material
that has
that has
at least one
at
of the
least one
three
of the three
dimensions. So we have
dimensions. So we
XYZ.
have
If
XYZ.
any one of the
If any one
dimension
of
is
the
in the
dimension is
scale
in
of
the scale of
range of 1 to
range of
100
1 to
nanometer,
100
then
nanometer,
only we will
then
say,
only we will
okay,
say,
we are
okay,
dealing
we
with
are
the
dealing with the
nanoscale regime.
nanoscale regime.
So
So
there are
there are
uh,
uh,
various scales like
various
we can
scales,
deal
like
with
we
the
can deal with the
micrometer, we can, so
micrometer, we
this is
can, so
the
this is
whole
the
table.
whole
What,
table. But
so 10 raised to
so
minus
10 raised
6
to
we are
minus
dealing with
6, we are dealing with
micrometer, 10 raised to
micrometer,
minus
10 raised
3
to minus
millimeter
3
scale.
millimeter scale.
So here we
So
are working
here
in
we are
this
working
region.
in this region.
Femto and pico are
Femto
also
and pico are
there.
also there.
Attoseconds lasers
Attoseconds
are
lasers are
generating, but why
generating,
are
but
we
why
not
are
dealing
we
with
not dealing with
such
such
large scale like
large
10 raised to
scale, like
minus
10 raised
12
to
and 10
minus
raised to
12 and 10
minus
raised to
15?
minus 15?
Because it's very
Because it's
difficult.
very
The
difficult.
structural
The structural
instability
instability
increases when we move
increases when
from
we
the
move
nano
from
to
the
femto.
nano to femto.
So there are
So
some
there are some
questions
questions which
is in the
is in the
this
this
worksheet
worksheet
of the last
of the
worksheet.
last
So
worksheet. So
after
after
understanding each and
understanding
every
each and
slide, we
every
can
slide,
easily
we can
answer
easily answer
one word answer
one word answer
for all of the
for all of
questions
the
if we
questions
have
if
go
we
through
have go
this
through this
slides,
slides,
And
And
so one by one,
so one
I
by
will
one,
talk
I will
about the
talk about
questions
the
on
questions
in
only
parallel
in
also.
parallel also.
So here,
So here,
the motive of
the
this
motive
slide
of
is
this
okay. We are
slide is
dealing
okay.
with
We are
in this
dealing with
range.
in this
Here,
range. Here,
different material
different
sizes are
material
shown at a
sizes are
different
shown at a
length scale.
different length scale.
So you can see
So you
that
can see
it's a
that
human
it's
hair.
a human hair.
So
So
which is of size
which is
of
of size
100
of the
micron.
100
Now
micron.
we are
Now
slicing
we
into
are slicing
100
into
times.
100
So
times. So
100 by
100 by
100, it is
100,
equals
it
to
is
1
equals to 1
micrometer. Then we are
micrometer.
again
Then we are
slicing
again
it 1000
slicing it
times, then it will
1000
give
times,
you
then
1
it will give you
nanometer.
1 nanometer.
So we
So
can't
we
directly
can't
see by
directly
naked
see by
eyes
naked eyes
in this
in
resin.
this resin.
For that,
For that,
several
several
instruments we need
instruments we
to
need to
visualize it.
visualize it.
So
So
suppose if we want to
suppose if we
see
want to
a
see a
100
100
micrometer
micrometer
patch, okay, so
patch. Okay,
we
so
can
we
see the
can see the
hair by
hair
optical
by
eye.
optical eye by
Optically,
optically.
we can
We
use
can use
microscope for 1
microscope for
micrometer
1
or 5
micrometer or
micrometer
5
size.
micrometer size.
But when we are
But when
moving
we are
from
moving from
micrometer to
micrometer
nanometer,
to
we can't see
nanometer, we
by
can't
naked
see
eyes.
by naked
For
eyes.
that, we
For
have
that, we have
various systems.
various
One of
system.
them it
One of
is
them it is
SEM, that is
SEM,
scanning
that is
electron
scanning electron
microscopy technique.
microscopy
In
technique.
this, we
In
are
this,
using
we are
the
using the
electrons that is
electrons that is
bombarding to the
bombarding to the
of the surface of the
surface of the
substrate,
substrate.
like our
The
chips,
chip,
like
our
it
chips,
can be
like it can be
silicon, it can
silicon,
be
it can
silicon
be
dioxide
silicon
or silicon
dioxide or
nitride,
silicon
whatever
nitride,
it is, but
whatever
it is
it is, but it
bombarding
is
with this.
bombarding with
And
this.
then through
And
the
then
back
through the
scattering or
back
secondary
scattering or secondary
electrons,
electrons, we are able to
see
see
the
the
1
1
nanometer
nanometer
scale bar.
scale bar.
So we will
So we will
discuss obviously
discuss
in detail
obviously
in the
in
next
detail in the
lectures.
next
Now we
lectures.
just
Now
want to
we just
focus on
want to
how
focus
the
on how the
properties are
properties
changing,
are
how the
changing, how the
nanomaterials are
nanomaterials are
classified, what is
classified,
the
and what are the
application, what is the
application and
need
what is
of
the
the
need of the
nanomaterials. So
nanomaterials. So
today's lecture is all
today's
about
lecture
that
is all
thing.
about that thing.
But we will
But we will we have a
we
detailed
will have a
we
detailed
will have a
discussion
detailed
on
discussion
these
on
techniques
these
also.
techniques
And I
also.
will
And
show
I will
you
show you
also like
also
what
like
in our
what
lab
in
we are
our
working
lab we
on,
are working on,
like how are we
like how are we
fabricating, what is the
fabricating, what is
fabrication
the fabrication
process, like
process, like
how the nano
how the
devices
nano
are
devices are
we are making
we are
using
making using
etching,
etching,
deposition process,
deposition
lift off,
process,
all
lift
of
off.
these
All of these
processes in one
processes
lecture I
in
will
one
deal
lecture.
with
I will
that.
deal with that.
So here we
So
are
here we are
transitioning from
transitioning
bulk to
from
nano.
bulk to nano.
So here you can
So
see
here you can see that this is a
10 centimeter
10
size.
centimeter size.
Obviously, what is the
Obviously, what is
definition
the
of the
definition of the
nanomaterial?
nanomaterial?
At
That
least one
at
of the
least
size
one
should
of
be
the size
lesser
should
than
be
the
lesser than
100
the
nanometer. It
100
should be in the
nanometer.
range of
Should be in
1
the
to
range
100
of 1 to
nanometer.
100 nanometer.
So here the size
So
is
here
10
the
and
size is
20
10 and
centimeter,
20 centimeter,
10 and 20
10 and
centimeters.
20
So obviously it
centimeters.
is
Obviously, it is
bulk material.
bulk material.
Now when we are
Now,
moving
when
from
we're
bulk
moving
to
from
nano,
bulk to nano,
you can see
you
that it
can see
is
that it
the
is the
particle
particle
size is
size
100
is
nanometer.
100 nanometer.
So you can see
So
the
you can
scale
see
bar
the
here.
scale
It
bar
is
here. It is
500
500
nanometer. The
nanometer.
scale
The
bar is,
scale bar
and
is,
this size is
and this
100
size is
nanometer.
100 nanometer.
So
So
obviously the two
obviously the
dimensions
two
are lesser
dimensions are
than
lesser than
100 nano.
100 nano.
It is in the range
It
of
is in
1
the
to
range of
100.
1 to 100.
And this is
And
the
this is
image
the
taken by
image
the
taken by the
using the
using
SEM,
the SEM
scanning
device,
electron
scanning
microscope.
electron microscopy.
You can't
You can't
see
see
this material by
this
your
material
eyes.
by your eyes.
So okay, so we
So
saw
okay,
the
so we
SEM
saw
how
the
it will
SIM,
look
how
like
it will
at
look
the
like
nano
at the
scale.
nano scale.
So we can
So
define
we
at
can
least one of
define
the
at
three
least one of the
dimensions
three
in the range of
dimensions
1
in
to
the range
100
of 1 to
nanometer,
100 nanometer,
and it
and
will
it
exhibit
will exhibit
obviously very
obviously
different
very
mechanical,
different
electrical, and
mechanical,
optical
electrical, and optical
properties from the bulk
properties from the
counterparts.
bulk counterparts.
So one thing I
So
want to
one thing I
mention it
want to
here.
mention it here.
Gold
So
nanoparticle,
gold nanopartic
that is
that is
so there is
so
one
there is one
emergent
emergent
classification of
classification of
materials,
materials,
TMDCs.
TMDCs.
So
So
anyone heard
anyone
about
heard about
TMDCs?
TMDCs?
This
This
transition matters
transition matters
dicalcogenize.
dicalcogenize.
Okay,
Okay,
so
so
these are the 2D
these are the 2D
materials.
materials.
So
So
what
the what
exactly
exactly
happens when we are
happens
moving
when we are
from the
moving
bulk
from the
to
bulk
nano?
to nano?
So
So
basically, there is
basically,
a
there is
very
a
much
very
large change
much
in
large change in
band structure.
band
Because of
structures.
that,
Because
all
of
these
that, all
property
these
changes, like
property changes,
electrical
like
and optical
electrical and
properties.
optical
So
properties.
when we are
So
dealing with
when
the
we are
bulk
dealing with the
material,
bulk material,
it exhibit
it
the
exhibit the
indirect band gap.
indirect band gap.
So through
So
indirect
through
band gap,
indirect band gap,
we can't
we
use it
can't
in
use it in
like
like
photonics.
photonics.
since we need
since
the
we need
direct
the
band gaps
direct
for
band gaps
the
for
working in the
the
optics.
working in the
But when
optics.
we are
But
moving
when we are
from
moving
bulk
from bulk
to
to
monolayer,
monolayer,
the band
the
structure
band
changes
structure
from
changes from
indirect to direct
indirect
band
to
gap,
direct band gap,
so that we can
so that
use
we
it's
can
a
use it's
highly
a highly
usable material
usable
in case
material
of
in case
optics.
of
So
optics.
like this,
So
the
like this,
property
the property
changes.
changes.
So when we
So
move
when we
from
move
bulk to
from
nano,
bulk to
and
nano,
we
and
are using
we are using
for the
for the
different
different
purposes. For
purposes.
example,
For examples,
if we
like
have the
if
gold
we have the gold
nanoparticles, we are using in
nanoparticles, we are
medical
using in
imaging. If
medical
we have
imaging. If we
carbon
have carbon
nanotubes, we are
nanotubes,
using in
we are using in
electronics and
electronics
materials.
and materials.
Similarly, TiO2,
Similarly, TiO2,
sunscreens and paints,
sunscreens
we are
and
using
paints,
this.
we are using
But
this.
on a bulk
But on a
level, we
bulk
can't
level,
use
we
these
can't use these
materials.
materials.
So
So
the one
the
very
one
nice
very
example
nice
is,
example is,
so we have a
so
wheat
we have
plant,
a
which is
wheat
the raw
plant, which is the
material.
raw
It's a
material. It's
bulk
a
thing.
bulk
When
thing.
we're grinding
When we're
it, it is
grinding it,
moving,
it is moving,
it is
it
converting
is
into
converting into
semolina,
semolina,
and the
and
product is
the product is
changing at each and
changing at
every
each and every
step.
step.
And
And
then we are
then if we are
moving from
moving from
wheat
wheat
depending upon the
depending upon
processing
the
technique,
processing
our
technique,
end
our
products are
end
changing.
products are changing.
So wheat
So
flour,
wheat
and then
flour, and then
we are
when we are
so the basically
so
the
the basically
properties
the
are changing.
properties are changing.
Then we are it is
Then it
converting
is
into
converting
refined
into
wheat flour,
refined wheat
which is
flour.
called
It
maida.
is
So you
called
can
maida.
see
So you
that
can see that
when we are
when
asked
we
for
are
the
asked for the
which is
which is
preferable for health,
preferable for
obviously
health,
wheat flour
obviously
is
wheat flour
preferable,
is
but the
preferable, but
raw
the
product is
raw
same.
product is same.
But
But
depending upon the
depending
particle
upon the
size,
particle
the
size,
properties
the
are getting
properties are
changed.
getting changed.
So from
So
bulk to
from
smaller
bulk to smaller
particles, food
particles,
property
food property
changes, and
changes,
product
and
is
product
changing
is
depending
changing
on the
depending on
whatever the process
whatever the
technique we
process
are using.
technique we are using.
So then the
So
next
then the
example
next
is,
example is,
uh,
uh,
so in a
so in a
ancient time,
ancient time,
the people were
the
using the
people were
silver
using the
spoon
silver
for feeding
spoon
a
for
newborn
feeding a newborn
baby. So what was
baby.
the
So what was
properties
the
of that?
properties of
It
that?
has the
It has the
antibacterial properties.
antibacterial properties.
So
So
and it was
and it was
non-toxic. It has
non-toxic.
a
As
it
a
is
it is
biocompatible also.
biocompatible also.
So
So
it is starting
it
from
is
the
starting
beginning,
from
but
the beginning, but
we were not
we were not
aware of that
aware of
science
that
at that
science
time.
at that time.
But now
But now
during research,
during
so
research,
like
so like
we were
we were
without this
without
knowledge,
this
we were
knowledge, we
using
were
the
using the
nice
nice
like silver
like
spoon
silver
instead of
spoon
steel
instead of
spoon or
steel spoon or
aluminum spoon.
aluminium spoon.
Similarly,
Similarly,
silver
silver
nanoparticles,
nanoparticles, it
uh,
protects
it protects the
it protects
body
the
to fight
body to
against
fight
the
against
bacterial
the
properties.
bacterial properties.
So the
So the
chosen
chosen
what to say, the
what is it?
chosen
The chosen
weapons were very
weapons were
nice
very
attached
nice
from the
attached
ancient
from the
times also.
ancient times also.
Yeah, so
Yeah. So
from this,
from this,
like we have
like we
one
have
question
one
in our
question in our
assessment sheet
assessment
also.
sheet
So
also.
what was the
So what was the
nanotechnology in the
nanotechnology in the
ancient world?
ancient world?
So this,
So this,
what is happening
what is
here? There
happening
are
here? There are
churches, like
churches, like
cathedrals in the
cathedrals
Europe.
in the
They
Europe.
were using the
They were using the
nanoparticles
nanoparticles
in
in
their
their
cathedrals. So the
cathedrals.
glass
So
will
the glass
appear
will appear
green when
green
it is
when it is
illuminated from the
illuminated from
outside,
the
and is
outside,
purple
and is
red when
purple red
illuminated
when
from the
illuminated
inside.
from the inside.
So it has the
So it has
same
the
glass
same glass
but different
but
color. So
different
how is
colors.
it
So how
happening?
is it happening?
So
So
it is.
it
So
is.
you can
So
see
you can
here.
see here.
Uh,
Uh,
so these are
so
all the
these are all the
application of the
application of the
nanotechnology. So first
nanotechnology.
is
So
gold
first
and
is
silver
gold and silver
nanoparticles we
nanoparticles
can use to
we can
produce the
use to
stained
produce the
glass
stained
window.
glass
Like
window. Like
it is there
it
in
is
Europe
there
with
in
all
Europe
the
with all
cathedrals are
the
using.
cathedrals are
So the
using. So
size
the
of the silver
size of the
space
silver
is
space
40
is
nanometers.
40 nanometers.
So
So
uh,
uh,
so these are all
so these are all
examples
examples
where we can
where
see
we
the
can see
size,
the
depending
size,
upon the
depending
size, the
upon the
color is
size, the
changing.
color is
So
changing.
here, if
So
the
here,
size is
if the
40
size is
nanometer
40 nanometer
and the
and
shape
the
is
shape
spheres,
is
so
spheres,
the
so
reflected
the
color is
reflected
dark
color
blue.
is dark blue.
Similarly, if we have
Similarly, if we
gold
have gold
nanoparticles
nanoparticles
and if the size
and
is
if the
50
size is 50
nanometer, the reflected
nanometer, the
color is
reflected
yellowish
color
green.
is yellowish gray.
Because
Because
when the size
when the
is
size
changing,
is changing,
the reflective
the
index
reflective
and
index and
the band
the
structure is
band structure
changing.
is
So
changing.
depending
So
upon the
depending
band
upon the
structure,
band structures,
the
the
absorption wavelength is
absorption
different
wavelength is different
as compared
as
with the
compared
bulk.
to the bulk.
That's why
That's
these
why these
colors,
colors,
reflected
the
colors,
reflected
we are seeing
colors,
the
we are seeing
different.
the different.
Then,
Then,
so we observe
so
that
we
simply
observe that simply
uh, the
uh,
shape, is,
the shape,
the size
the
of
size
particle is
of particle
changing,
is
and the
changing
properties
and the
are also
properties sizes also changes.
So
So
next from the
next
table
from the
is
table
we were
is we were
seeing that why
seeing
not pick
that
or
why not
femto
peak or
materials? Why
femto
are we
materials? Why are we
only
only
interesting in the
interesting in the
nanomaterials, not beyond
nanomaterials,
that?
not beyond that?
So
So
it is
it is
sorry.
sorry, huh?
So the scale
So
is
the
too
scale is
small.
too
So
small. So
in
so
SCM
in
techniques
SCM
in
techniques
EBL,
in
so
EBL,
we are
so
using
we are using
electron beam
electron beam
lithography
lithography
or
or
focused ion beam
focused
milling
ion beam milling
or using
or
laser
using laser
interference. We are using
interference. We
these
are using
techniques
these
for
techniques
making
for
the
making the
sizes
sizes
like 50
like
nanometer
50 nanometer
feature size, 10
feature size,
nanometer
10
feature
nanometer
size.
feature
We are
size.
using
We
these
are using
techniques.
these techniques.
But
But
beyond that,
beyond that,
we are dealing
we
with
are
the
dealing with the
subatomic levels,
subatomic
like
levels,
at level of
like at level
proton,
of proton,
electron. So
electron. So
which is
we,
not
which is
practical
not
for us.
practical for us.
At a human
At a
level, it is
human
not
level, it is
practical to
not
engineer
practical
all
to
these things
engineer all
using
these things
these,
using these,
even with the
even with
EBL
the
also.
EBL also.
That's why
So
we are
that's
not
why we are not
going.
going,
We can't go
we
beyond
can't go beyond
nano materials,
nano
and
materials,
that's why we are
and
not
that's
dealing
why we are
with
not
pico
dealing
and
with
femto.
pico and femto.
Then what is the
Then what is
quantum
the quantum
dominance?
dominance?
So when we are
So
moving
when we are
from
moving
beyond
from
nano,
beyond
the
nano,
quantum
the quantum
uncertainty and the
uncertainty and
tunneling
the
effects
tunneling
that is
effects
happening
that
in the
is happening in the
subatomic levels,
subatomic levels,
that also
that also
dominating, and it is
dominating, and it is
making for
making for
human to
human
difficult
to
to control
difficult
or
to
design
control or design
materials.
materials.
Third is current
Third is
technology
current
limitation.
technological
This is
limitation.
what I was
This is
talking
what I
about
was
when
talking
we are
about, that
dealing
when
with
we are
the
dealing with the
nano size
nano size
devices. We are using
devices, we are
electron
using
beam,
electron beam
and
lithography.
at
And
electron beam
at electron
lithography,
beam
we
lithography,
can't go
we
beyond
can't
the
go
10
beyond the
nanometer
10
feature
nanometer
size.
feature size.
Although we are
Although
dealing
we
with
are
the
dealing with
higher
the
kV,
higher kV,
so we are
so
working on
we are working
20
on
kV,
20
50
kV,
kV.
50 kV.
Even after using
Even after
100
using
kV, we
100
can't
kV,
go
we
beyond
can't go beyond
1 nanometer
1
feature size.
nanometer feature size.
So
So
according to the
according to
present
the
technology,
present
we are not
technology, we
able
are
to
not able to
fabricate
fabricate
at the
at
pico
the
and femto
pico and
scale.
femto scale.
And also
And
the
also
last
the
reason is
last
this
reason is this
stability of the
stability of
structures.
the structures.
We can't,
We
because we are
can't,
dealing with
because
the
we are dealing with the
subatomic levels.
subatomic levels.
There is no
There is no
structural
structural
stability at
stability
femto
at
and pico
femto
scale.
and pico scale.
So
So
uh,
uh,
in the
in the
1960,
1960,
so Richard
so
Feynman
Richard
delivered a
Feynman
lecture with the
delivered a lecture
title
with
"There
the
is
title "There
Plenty
is
of Room
plenty
at
of
the
room
Bottom."
at the bottom."
So
So
where he
where
indicated
he
that the novel
indicated that the
physics
novel
which can
physics, which
evolve if
can evolve
nanosized
if
particles
nano-sized
are
particles are
investigated carefully.
investigated carefully.
So
So because
what was
what was
the
the
what he is
what he is
emphasized that
emphasized, that
physics doesn't
physics
prohibit
doesn't
nanoscale
prohibit
engineering,
nanoscale engineering,
limits are
limits are
technological, not
technological,
theoretical.
not
At a
theoretical. On
theoretical
at a
level, we
theoretical
can go
level, we
beyond.
can go beyond.
But on
But on
technological level, I
technological level,
mentioned
I
that
mentioned
using
that
electron
using
beam
electron
lithography,
beam
we can't go
lithography, we
beyond
can't
this.
go beyond this.
So
So
this is the
this is the
uh,
uh,
this is the one
this is
thing
the one thing
that
that
we don't
we
have
don't
the
have the
much
much
technical
technical
advantage to
advantage
be
to
go
be
beyond that.
go
That's
beyond
why
that.
we
That's why
stopped
we
at the
stopped at the
nanoscale.
nanoscale.
One nice thing
One
is
nice
here
thing
is
is
this. So
here is
this
this.
is
So this is
AFM. AFM
AFM.
is atomic
AFM is
force
atomic force
microscopy.
microscopy.
So what we
So
do
what
using
we do
this,
using this,
uh,
uh,
so
so
in
in
AFM we can
AFM,
see
we
these
can
gold
see these gold
nanoparticles.
nanoparticles.
What is happening
What is
here?
happening here?
Here there is a
Here there is a
cantilever tip.
cantilever
The
tip.
laser will
The
excite,
laser will
and
excite,
after
and after
exciting on
exciting
this
on this
cantilever
cantilever
and tip, the light
and
will
tip, the
deflect.
light will
So
deflect.
here the
So
light will
here the
deflect
light
from
will
this
deflect from
size,
these sides,
and then it
and
will
then
fall
it
on
will
my
fall on my
surface.
surface.
It will
It will
generate
generate
a
a
signal that will
signal that
directly
will
go to
directly go to
photodiode,
photodiode,
and
and
it can give us
it
the
can give us
AFM
the
image
AFM image
according to the
according
particle
to the
size, and
particle
that
size,
we
and
can
that
go
we can go
also up to 10
also up to
nanometer
10
only.
nanometer only.
Which
Which,
so what
so
does
what
AFM
does
do? It can
AFM do?
give
It
us a
can give us a
high resolution
high
3D
resolution
surface, just
3D
like
surface, just like
STM.
STM.
So STM is
So STM
scanning
is
tunneling
scanning tunneling
microscopic images.
microscopic
So
images.
we can
So we can
manipulate
manipulate
individual atom, we
individual
can
atom,
see.
we can see.
And
And
so these are
so
several
these are several
examples like
examples,
isolation
like
of
isolation
graphene.
of graphene.
So we know
So
that
we know
it
that
is the first
it
to
is the
be
first to be
material,
material
which
which
is metallic
is
and it
metallic
shows
and it
the
shows
high
the high
conductivity also.
conductivity
Then
also.
carbon
Then carbon
nanotubes, these are
nanotubes,
ultra
these are
strong
ultra
and
strong and
conductive
conductive
nanomaterials.
nanomaterials.
So,
So
so we
so we like
for
for
like
like
comparing for
comparing
looking in
for
the
looking
particle
in the
sizes
particle
of
size
the
of
gold
the gold
nanoparticles and silver
nanoparticles and silver
nanoparticles.
nanoparticles, we do
First thing
first
SEM
thing
scanning
SEM
electron
scanning electron
microscopy, then we
microscopy,
do
then we do
TEM
TEM
turning electron
turning
microscopy,
electron
then we
microscopy, then
do
we
AFM
measure
also, that
AFM
is
also,
atomic
that is
force
atomic
microscopy.
force
In
microscopy.
all these
In all
devices,
these devices
uh,
we can
solve
resolve
to
up
10
to
nanometer
10
feature
nanometer
size.
feature size.
But beyond that,
But beyond that, we are not able to do.
so
So
these are
these
some
are some
properties,
properties,
and
and
because of that,
because of that,
properties
these
only,
properties
we are
only,
able to
we are
see
able to see
the changes
the
when we are
changes
moving
when we are
from bulk
moving
to
from
nano.
bulk to
The
nano.
first is
The first
enhanced
is
surface to
enhanced
volume
surface to
ratio,
volume ratio,
and second
and
is low
second is low
density.
density.
Third is reduced
Third is
transport
reduced
length for
transport
mass and
length for
charge
mass and charge
transport.
transport.
Fourth is high
Fourth is
surface
high
area,
surface area,
then low mass
then low
requirement
mass
and reduction
requirement
in
and
cost.
reduction in cost.
So we
So
can see
we
that
can see that
how the
how
surface
the
to
surface to
volume ratio
volume
changes.
ratio
So
changes. So
surface area is
surface
given by
area is given
4 pi
by
r
4
square.
pi r square.
Volume is 4 by
Volume is
3
4
pi
by
r
3
cube if
pi
we
r
are
cube
having
if
a
we are having a
sphere.
sphere.
If we divide
So
by
if we
s by
divide by
b,
s by b,
it will give us 3
it
by
will give
r.
us 3 by r.
So now we
So
can see
now we
that
can see that
effect of,
effect of,
so if the
so if
diameter
the
will
diameter will
increase,
increase,
the surface
the
to volume
surface to
ratio
volume ratio
will decrease.
will decrease.
So
So
the small
the
size
small size
nanoparticle,
nanoparticle,
the surface to
the
volume
surface to
ratio
volume
will
ratio
increase.
will
Oh,
increase.
you
Oh,
can see in
you
this
can
also.
see in
Okay.
this also.
So
Okay.
change in
So
surface
change in
area for
surface area for
uh,
uh,
this is a
this
sphere.
is a
So
sphere.
surface
So
area will be
surface
4
area
pi
will
r
be 4
square
pi r
and the
square,
volume is
and the
given by
volume is
4 by
given
3
by
pi
4
r
by 3
cube.
pi r cube.
Surface to
Surface
volume
to volume
3 by r. So
3
you
pi r.
can
So
see that
you can see
as the
that
size
as the
is
size is
increasing,
increasing,
surface to volume
surface to
ratio will
volume ratio will
decrease.
decrease.
Now, what
Now,
is high?
what is
What is
high?
the
What is the
advantages of
advantages of
devices with high
devices with
surface
high
area?
surface area?
So the
So the
change
change
of size of
of size of
nanoparticles cause the
nanoparticles
change.
causes
Obviously, it
change.
will change
Obviously,
the
it will change
intrinsic
the
properties
intrinsic
of the
properties of
materials,
the
like we
materials,
discussed in
like
the
we
first
discussed in the
slide.
first slide.
Melting
Melting
point. So melting
point. So
properties,
melting
electrical
properties,
conductivity,
electrical
mechanical
conductivity,
strength.
mechanical strength.
So from bulk
So
to
from bulk to
nanoparticles,
nanoparticles,
this
this
increase
increase
if the
if the
mechanical strength
mechanical
is
strength
large.
is large.
Obviously, it will
Obviously,
increase
it will
the
increase
performance
the
of the
performance of
devices.
the devices.
Next is
Next
color.
is color.
So this is
So this
example
is
of
example
cadmium
of
sulfide
cadmium sulfide
nanoparticles. You can see
nanoparticles.
that
You
if
can
the
see
size is
that if
2
the size
nanometer,
2 nanometer,
the size is
the
different.
size is
If we are
different.
moving
If
from
we are
2 to
moving
6
from 2 to
nanometer, you
6
can
nanometer,
clearly
you
see
can
the
clearly see
change.
the change.
Now,
Now,
what is the
what
need
is
of
the need of
nanoparticles? It
nanoparticles?
is
It
in the
is
field of
in the field of
electronics,
electronics,
which is faster
which
and
is
smaller
faster and
devices,
smaller
obviously.
devices, obviously.
So,
So
as you can see
as
now,
you
the
can
chips
see
are
now, the
coming.
chips
There
are
are
coming. There are
hundreds of thousands
hundreds of
of
thousands of
transistor on a
transistor
single chip,
on a
which is of
single
the
chip, which
size
is
of
of the
only
size of only
1 mm.
1 mm.
So you can
So you
think
can
about
think about
and how fast
and
it is
how
working.
fast it is
All
working. All
possibilities because
possible
of
it is because of
nanomaterials,
nanomaterials only.
and we are using
And we
in
are using in
as
as
energy
solar cells,
supercapacitors. We are
supercapacitors. We are
forming fuel
forming
cells,
fuel
and
cells,
in
and in
medical we can
medical we can uh,
do the
do the
direct targeted
direct
drug
targeted
delivery,
drug
cancer
delivery, cancer
therapy,
therapy,
endoscopy. That is a
endoscopy. That is a
part of advanced
part of
imaging
advanced
only.
imaging only.
Also, in
Also,
optics,
in
we are doing
optics, we are
optical
doing
sensor,
optical sensor,
quantum imaging.
quantum imaging.
We
We
can
can
also
also
do
do
optoelectronics,
optoelectronics,
and
and
at a
at a
construction level,
construction level,
if the
if
mechanical
the
strength
mechanical
will be
strength will
higher,
be
it
higher,
can be
it
used
can
for
be
the
used
stronger
for
and
the stronger
self-healing
and
materials.
self-healing
So
materials.
these are
So
all the
these are all the
advantages of the
advantages of the
nanomaterials in the
nanomaterials in the
various fields.
various fields.
Yeah. So
Yeah.
next,
So next,
in
in
in the first
in the
part, we
first
only
part, we
talked
only
about
talked about the
what is meant
what
by
is meant by
nanomaterials
nanomaterials,
and what is the
and what is the
applications and
applications,
what
and
properties
what
are
properties
changing
are changing
from bulk to
from
nano.
bulk to nano.
So we saw
So we
that
saw that
there are
there are
changes in the major
changes in
six
the major six
properties. One is
properties. One
surface
is
to
surface to
enhance surface to
enhance
volume
surface to volume
ratio.
ratio.
Also, these are
Also, these are
uh,
uh,
cost reduction
cost
also
reduction
is there.
also is there.
And
And
now
now
we will talk
we
about
will
the
talk about the
classification of
classification of
nanomaterials.
nanomaterials.
So
So
we know that there
we
are
know that there are three
dimensions,
dimensions,
and
and nanomat
all
first
the
of all the
nanomaterials can
nanomaterials
be
can
classified
be
on the
classified
basis of
on the basis
origin,
of
dimension,
origin, dimension, and
composition. So
composition.
based on
So based
origin,
on origin,
there are
there are defined as natural,
incidental, and
incidental, and
artificial
artificial
nanoparticles.
nanoparticles.
So
So
where can we found
where
the
can be
natural
found the natural
nanomaterials? So
nanomaterials?
natural
So natural
nanomaterials,
nanomaterials,
uh,
uh,
like that we are
like
not
that we
forming
are not
without
forming
human
without human
where are
intervention.
these
Where are these
forming? So it can
forming?
be
So it
formed
can be formed
through
through
physical, chemical,
physical, chemical,
geological,
geological,
biological
or biological
processes.
processes.
So you can see
So
in
you can
this
see in this
image,
image,
it's a
it's
volcanic shoot
volcanic
particles.
shoot particles.
So
So
obviously you can't
obviously you can't
see
see
directly like this, but
directly like this, but in
using the
using
scanning
the
electron
scanning
microscopic
electron
technique, you
microscopy
can see.
technique, you can
So you
see.
can see
So you
here
can see here,
uh,
uh,
in the SEM,
in the
you can
SEM, you
clearly see.
can
So this is
clearly
the
see. So this is
scale
the
bar of 10
scale bar of
micrometer.
10 micrometer.
So
So
this whole length
this
from
whole
here to
length from
here it is
here
10
to here, it is 10
micrometer. So
micrometer.
this
So
size is
this size is
approximately 10
approximately
nanometer.
10 nanometer.
From here to
From
here,
here to here,
10 to 100
10 to
nanometer
100
it can be.
nanometer it can be.
So,
So,
and these
and
materials
these
exist
materials
everywhere,
exist everywhere, like
hydrosphere,
hydrosphere,
lithosphere,
lithosphere,
biosphere.
biosphere.
So we have
So we have
minerals,
minerals,
matters,
matters,
oxides, and
oxides,
other
and
composites
other
where
composites
there is no
where
human
there is no
intervention.
human
Still,
intervention. Still,
these processes
these
are
processes
happening,
are
and we
happening,
have
and we have
the
the
nanomaterials.
nanomaterials.
Then,
Then,
on the basis of
on the basis of
geological,
geological,
so volcanic
so
eruption
volcanic
and
eruption and
minerals
minerals
precipitation.
precipitation,
For example,
for
clay
example,
materials
clay
and silicon
materials and silica
nanoparticles, obviously.
nanoparticles, obviously.
Then, through the
Then through the
atmosphere,
atmosphere,
dust storms,
dust
sea
storms,
sprays,
sea sprays,
uh, forest
and
fires,
forest fires,
all in these
all in these
processes, the
processes, the
nanomaterials are involved.
nanomaterials are involved.
Then, through the
Then through the
biological
biological
processes,
processes,
they are produced
they
by
are
the living
produced by the living
organisms like
organisms like
microbes, plants,
microbes, plants,
animals.
animals.
So,
So
the
the calcium
carbonate
calcium
in sea
carbonate
cells
in
and
sea cells and coral
protein
protein
nanostructures.
nanostructures.
And then the
And
last
then
case
the
is
last
natural
case is
organic
natural organic
nanomaterials.
nanomaterials,
Obviously, biological
obviously
decay. So
biological
there
decay. So
also there
there
is
also
degradation
there
of
the degradation,
when the natural
when the
organic
natural
matter
organic matter
goes in soils
goes
and
in
waters,
soils and waters,
the
the
decomposition process
decomposition
start and
process
it is
start, and it
moving
is moving
towards the
towards the
nanomaterials.
nanomaterial
So
size.
these are all
So these are all
natural things. Then
natural things. Then
incidental thing, what
incidental
we do.
thing, what we do.
So
So
we are doing.
we are doing
Uh,
uh,
so we are
so we are
uh,
uh,
engineering the
engineering the
particles.
particles.
Like
Like
we have,
we have,
suppose
suppose
earlier
earlier we were
we were
talking about in the
talking about
past
in the
that
past
we
that
have
we
the
have
chips
the
from
chips
10
from 10
micrometer to
10
100,
micrometer
10
to 1
micrometer to
mm.
1 mm.
Now we
Now we
intentionally designed
intentionally
our
designed our
structures
structures
and the
and the
dimensions such that
dimensions
we
such
can
that
work
we can
the
work
same
the
process
same
on a
process on a
nanoscale.
nanoscale.
So we
So we
started
started
playing with the
playing
silicon
with the
photonics,
silicon nitride
photonics, and
photonics,
we
and
are
we are
moving towards the
moving towards the
technological development
technological development
such that we
such
can
that we can
go from
go
that
from
scale
that
to
scale to
10 nanometer
10
or 100
nanometer or
nanometer
100
scale.
nanometer scale.
So
So
this is
this is
so
so
basically
basically
byproducts of
byproducts
human
of human
activities. So that
activities. So
includes like
that includes like
combustion, industrial
combustion,
processing,
industrial processing,
and chemical
and chemical
reactions, and
reactions,
how they are
and how
different
they
from
are differ
engineered
from engineered
nanomaterials. They are
nanomaterial. They are
uncontrolled. We are
uncontrolled.
doing in
So
a
we are doing in
controlled
a
way.
controlled way.
That is called
That is called
engineered
engineered
nanomaterials.
nanomaterials.
And if
And
that is
if
the
that is the
uncontrolled way, but
uncontrolled way, but
the
the
nanomaterials are
nanomaterials
forming
are
by the
forming
human
by the
intervention
human intervention
and
and
unregulated products of the
unregulated
human
products of the
operation.
human
That is
operation,
called
that is called the
incidental
incidental
nanomaterials. So
nanomaterials.
basically, these
So
are not
basically, these are not
engineered but
engineered
generated
but
as
generated as
bioproducts. The
bioproducts.
size
The
ranges
size
from
range
1 to
is from
100
1 to
nanometer,
100
and the
nanometer, and the
morphology is
morphology
irregular
is
because
irregular
we are
because
not
we are not
controlling that.
controlling that.
And then
And
through
then through
chemical
chemical
composition, it
composition,
is
it
carbon,
is carbon,
metals,
metals,
oxides, sulfates, and
oxides, sulfates,
nitrates.
and nitrates.
So similarly,
So
there are various
similarly, there are various
properties.
properties like
Highly
highly
polydispersed size and
polydispersed in
shape
size and shape
because we don't have
because
any
we don't
control
have
on
any
their size
control on
and
their
the
size
shape.
and the shape.
And surface
And
chemistry,
surface
they will be
chemistry, they will
reactive,
be
oxidized,
reactive,
and
oxidized, and
since
since
they can
they can be
contaminated with
contaminated with the
hydrocarbons or metals
hydrocarbons
through
or
the
metals
environment.
through the
Now
environment.
this is
Now this is
engineered
engineered where we are deliberately designed our
nanostructures. In
nanostructures
the
in
whatever
the
the design
whatever the designed
desired range,
desired
we can
range, we can
synthesize, design,
synthesize,
and
design,
structure.
and structure.
So these
So
have the
these have the
size
different
dependent
size
properties
dependent
for
properties for
specific
specific
applications,
applications,
science, industry,
science,
and medicine.
industry, and medicine.
So these
So these
materials
materials
differ from
differ from
natural and
natural and incidental
nanomaterials by intention
nanomaterials
of
by intention of
application. We
application.
have the
We have
full
the
control,
full control,
structure, shape, and
structure, shape, and
composition,
composition,
and then
and then
depending upon
depending
the
upon the whatever is our
motto. So
motto.
suppose if we
So
are
suppose
dealing
if we are
with
dealing with
medicine,
medicine,
it will have
it
some
will be
different
have some
solar
different
cells,
size. Solar
have
cells,
some
it will
different
have some different
features. Like
feature
suppose
size.
we
Suppose
want to create
we
the
want to
lasers
create
on
the
chip,
lasers on
we will
chip,
deal with the
we will deal with
micrometer
the
size.
micrometer size.
So
So depending upon the
application, we
application,
can
we
control
can
the
control
structure,
the
shape, and
structure, shape,
composition.
and composition.
So
So
now this
now
was the
this was the
classification of
classification of
nanomaterials based on
nanomaterials
the origin.
based on the origin.
Now the
Now the
classification is based
classification
on
is
the
based on the
dimensions.
dimensions.
So
So
on the basis of
on the basis
dimension,
of
it is
dimension, it is
classified
classified
as
as
into four
into four
categories:
categories:
0D, 1D,
0D,
2D,
1D,
3D.
2D, 3D.
So
So
it is based
it
on
is
their
based on
physical,
their physical,
chemical, and
chemical,
function
and
properties
function
like
properties
surface
like
area,
surface
quantum
area,
effects,
quantum
electrical
effects,
and
electrical and
magnetic properties.
magnetic properties.
So when we
So
are talking
when we are
about
talking
0D,
about 0D,
so we have three
so we have
dimension
three
X, Y,
dimension
and
X,
Z.
Y, and
When
Z.
all the
When
three
all the
sizes are
three
lesser
sizes
than
are lesser than
100 nanometer,
100
that we
nanometer,
call the
that we call the
zero dimensional
zero dimensional
nanomaterials.
nanomaterials.
So
So
no dimension,
no dimension,
length, width, and height,
length, width, and height,
all are in the
all
range
are in
of
the range of
nanoscale. So
nanoscale.
for example,
So
we
for
have the
example, we
quantum
have the
dots.
quantum dots.
CDS is that is
CDS, that
cadmium
is cadmium
sulfide, lead
sulfide,
sulfide, or
lead
indium
sulfide, or
phosphide
indium
quantum
phosphide
dots,
quantum dots,
which we
which we
so depending
so
upon the
depending
size
upon
of
the
these
size of these
nanoparticles, the
nanoparticles,
emissions
the
are
emissions
at
are
different
at
rates.
different rates.
So when we
So
work on
when we
labs,
work
when
on
we want
labs,
to
when
see
we
the
want to
PL,
see the PL,
PL is
PL is
photoluminescence. So
photoluminescence. So
depending upon
depending
the
upon
size
the
of the
size
quantum
of the
dots, we can
quantum dots, we
tune
can
from the
tune from the
suppose
suppose you want to
photoluminescence and
photoluminescence
500
and
nanometer,
500
you will
nanometer,
change the
you
size,
will
you will
change
tune
this,
the
you will
size.
tune the size.
If you want the
If you
emission
want the
at
emission at
580 nanometer,
580 nanometer,
you will
you
change
will
the size
change the
according
size
to
according to
that emission.
that emission.
So this are
So this are
we are dealing with
we are
the
dealing with the
tunable
tunable PL
when we are dealing with
when we are
the
dealing with
quantum
the
dots.
quantum dots.
So also
So
we have
also we have
silver
silver
nanoparticles, gold
nanoparticles, gold
nanoparticles,
nanoparticles,
and in
and in
case of 0D,
case of 0D,
in all the
in all the
dimensions there will be
dimensions, there
quantum
will be
confinement,
quantum confinement,
which will result in
which will
size
result in
dependent
size
optical and
dependent optical
electronic
and electronic
properties.
properties.
So this we
So
are
this
using
we are
solar
using in
cells,
solar cells,
bioimaging,
bioimaging,
energy storage
energy
application.
storage application.
So when we are
So
dealing with
when we are dealing
1D,
with
so
1D, so the
1D meaning
1D meaning
if
if
only one
only
dimension
one
is
dimension
greater
is
than
greater
100
than
nanometer,
100
but
nanometer,
in the other
but
two
in the other
dimension,
two
it is
dimension,
of the
it is of
nanoring,
the
that is lesser
nanoring,
than
that
the
is
10
lesser than the
100
10
nanometer.
100 nanometer.
So then what will
So
happen?
then what will happen?
So in
So
0D,
in 0D,
XYZ,
in XYZ,
properties
the
were same
properties were
because the
same
size
because the
was
size
same
was
in the three
same in the
directions.
three direction.
Now,
Now,
in one
in
direction, the
one
size is
direction, the
large.
size is
So
large.
obviously,
So
there will be
obviously,
some
there will be some
anisotropic behavior.
anisotropic behavior.
Now, depending
Now,
upon in
depending
which
upon in
direction
which
we are dealing
direction
with,
we are
the
dealing with,
properties
the
will change
properties will
according to the
change
direction.
according to the direction.
For example,
For
we
example,
have
we have
carbon nanotubes.
carbon
So you can
nanotubes.
see the
So you can
SEM
see the
images of
SEM
carbon
images of
nanotubes,
carbon nanotubes,
which is
which
known for their
is known
high
for their
strength
high strength and
nanoconductivity. So
nanoconductivity.
when we will
So when
see
we will see
only in
only
particular
in particular
direction, it
direction,
is
then
larger
it
than
is
100
larger than
nanometer.
100 nanometer.
But
But
this
in this
direction and
direction
in the
and
height
in the
direction,
height
it is
direction,
lesser
it
than
is lesser than
100 nanometer. So
100
there is
nanometer. So there is
an
an
anisotropic behavior.
anisotropic behavior.
But
But
high, we will get the
high, we
high
will get the
aspect
high
ratio,
aspect ratio,
obviously,
obviously,
and then
and then
it is
it
efficient
is
in
efficient
charge
in
transport.
charge
That's why
transport.
we use
That's why we
carbon
use
nanotubes in
carbon nanotubes
transistors
in
and
transistors and
supercapacitor.
supercapacitor.
Then 2D.
Then 2D.
So
So
when we would talk
when we
about
would talk
2D,
about
it
2D,
means the
it
size
means the
is
size
in two
is in two
dimensions greater
dimensions
than
is
100
greater than
nanometer,
100
but
nanometer,
only in one
but only
direction
in one
it is
direction is lesser than
100 nanometer.
100 nanometer.
So we
So
can
we can
characterize
characterize
it by sheet.
it by
So
sheet.
we can see
So
here.
we can see here.
There was one
There was
image.
one image.
Um,
So
Okay, maybe we'll come.
Maybe we'll come.
So when we were
So
when I was talking
when I was
about
talking about
graphene
the
or
graphene or
TMDCs, the
TMDCs, the
confinement that
confinement
are 2D
that are
materials
2D
only in
materials, only in
one direction
one
there was
direction there was a
quantum confinement
quantum
or the
confinement,
size
or
is
the
lesser
size
than
is lesser
100
than
nanometer.
100
So
nanometer.
there was
So there was
large area to
large
volume
area to
ratio and
volume
it will
ratio, and
provide
it
us
will
the
provide us the
energy
energy
storage,
storage,
change in the
change in
electrical
the
and
electrical
optical
and optical
properties.
properties.
In 3D,
In 3D,
all the three
all the
dimensions
three
are greater than
dimensions are greater
100
than
nanometer,
100 nanometer,
but
but
made of
made of
nanoscale building
nanoscale
blocks or
building
features.
blocks or
So
features. So
confinement is not in
confinement
any
is not in
direction,
any
obviously
direction,
because
obviously,
in all the
because
three
in all the
direction
three
the dimensions
directions
are
the
greater than
dimensions are
100
greater than
nanometer.
100 nanometer.
So we can
So we can
uh,
uh,
so we can
so we
use
can use
it.
it.
So it
So
has a
it
combined
has a
feature,
combined feature,
bulk and
bulk
nanoscale
and
behavior,
nanoscale
which can
behavior,
be used
which
for
can be used for
coating, structure
coating,
materials,
structure
and gas
materials, and
storage.
gas storage.
Then
Then
origin is
origin
done
is done
class
class
the base of
on the base
dimensions
of
is done.
dimensions is
Now
done.
the based on
Now the based on
composition, whether these are
composition, whether
carbon
these are
based
carbon
materials,
based
metal based
materials, metal
materials,
based materials,
dendrimers,
dendrimers, and
composites. So
composites.
in
So
case of
in
carbon
case
based
of carbon
materials,
based
it
materials,
is
it is
composed of carbon,
composed of carbon,
which will take the
which will
form of
take the
hollow
form of
spheres,
hollow
ellipsoids,
spheres,
or tubes.
ellipsoids, or tubes.
So we can see the
So we
example
can
of
see the example of
C60 that is
C60, that is
fullerenes, while
fullerenes,
cylindrical
while
forms are
cylindrical
called
forms are
nanotubes.
called nanotubes.
Now metal.
Now metal,
So when we are dealing
so
with
when we are dealing
metals,
with
we see
metals, we
quantum
see
dots,
quantum dots,
nano gold and
nano
nano
gold and
silvers,
nano
and
silvers,
metal
and
oxide
metal
TiO2.
oxide TiO2.
Then
Then
dendrimers. So
dendrimers.
here
So
dendron
here
means
dendron
tree,
means tree,
and it is a
and it is
Greek
a
word.
Greek word.
So it is
So it
clearly
is clearly
dendrivers. Dendrimers means
dendrimers means
branched
repetitively
molecules.
branched
So
molecules.
these
So these
nanomaterials and
nanomaterials
nano-sized
and nano-sized
polymers built from the
polymers built
branched
from the
units,
branched units,
and
and
the
the
surface
surface
have a
will
numerous
have a
chain
numerous
ends
chain
which can
ends
perform
which can
specific
perform specific
chemical functions.
chemical functions.
So this
So this
is since it
is,
has a
since it
chain of
has a chain of
molecules, and
molecules, and
depending upon how
depending
long
upon
the
how
chain
long the
is,
chain is,
it can
it
perform
can
specific
perform
chemical
specific
functions. So
chemical functions.
people are
So
using
people are using
mostly for the
mostly for the
drug delivery
drug
and the
delivery and the
nanosensing.
nanosensing.
Then
Then
composites are,
composites
it is
are,
a
it
combination
is a
of
combination of
nanoparticles. So you can see
nanoparticles. So you
these
can
are
see
all
these are all the
semi images, and
semi
this is
images,
a
and this is a
fractal fractal shape.
fractal
So
shape.
if you
So
will
if you will
zoom into
zoom
more,
into more,
you will find
you
the
will
same
find the
shape.
same shape. So
It will have
it
the
will have the
highest
highest
mechanical
mechanical
and thermal
and
strength,
thermal strength,
so that we are
so that
using
we are
for
using for
packaging
packaging
materials.
materials.
So
So
next, is why is
next,
the
why is the
need of
need of
nanomaterials?
nanomaterials?
So okay,
So okay,
so you can see
so you
this.
can see this.
It is
It is
3D.
3D.
So in
So
all the
in
three
all the three
dimensions, we have
dimensions, we have
the size
the
greater than
size
100
greater than the
nanometer,
100 nanometer,
and then
and then
it's a
it's a
nanotube,
nanotube,
1D. So
1D.
one
So
dimension
one
is getting
dimension is
reduced.
getting
So
reduced.
first we
So
have
first
bulk.
we have bulk.
When one we
When
will talk
one
about
we will talk
1D, it will
about 1D,
convert
it
into
will
well,
convert into well,
and then
and then
when
uh,
we'll move
when
from
we'll
1D
move
to
from
2D, it
1D
will
to
convert
2D, it
into
will convert
wire,
into wire,
and then
and
it
then
will convert
it will
into dot.
convert into dot.
So
So
we saw
we
that
saw that
why are they
why are
important?
they important?
It
It
will
will
change the
change
mechanical
the mechanical
property,
property, thermal property,
magnetic properties,
magnetic
optical
properties, optical
properties,
properties,
and it has
and
the
it has the
various
various
applications.
application.
So
So
just a second.
just a second.
So
So
let's
let's
take
take
for
for
10
10
minutes
minutes
break
break
here.
here.
After that, I
After
will
that, I will
restart.
restart.
So
So,
okay, now
okay,
let's
now let's
resume the
resume the
lecture.
lecture.
So I
So,
have
I
a few
have a few
questions
questions
from
from
the
the
whatever I took
what I told you
right now.
right now.
So we
So,
saw
we
that
saw
when we
that
are
when we are
moving from
moving
bulk
from bulk
to
to
nano
nano
size,
size,
so we are
so we
seeing
are
that
seeing
the
that the
surface
surface
atoms
atoms
are
are
possessing the
possessing the
higher
higher
potential
potential
energy,
energy,
like they are
like they are
highly
highly
reactive.
reactive.
So that's
So
why we
that's
are
why we
able
are
to
able to
use
use
in
in
like
like
hydrogen fuel
hydrogen fuel
cells.
cells.
So why
So
is
why
this
is this
happening?
happening?
Like why do
Like why do
surface
surface
atoms
atoms
possess
possess
higher
higher
potential
potential
energy
energy
compared to the
compared to
bulk
the bulk
atom?
atom?
Okay,
Okay,
so we
so we
saw
saw
that
that
what is
what is
happening in
happening
bulk
in bulk
atoms. So
atoms.
in
So
bulk
in bulk
atoms,
atoms,
when we are
when we
saying
are saying
these are
these are
fully surrounded
fully
with this
surrounded,
layer,
this
layer,
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 layer, layer,
complete 3D
complete 3D
structure.
structure.
So bulk
So bulk
atoms are
atoms
fully
are fully
surrounded by
surrounded by
neighbors, like
neighbors,
high
like high
coordination
coordination
numbers
numbers,
with
with
failed
failed
chemical
chemical
bonds.
bonds.
So
So
it when the
when the
bonds are
bonds are
completely filled,
completely filled,
that will be
that will be a
stable
stable
state,
state,
lower
lower
energy state.
energy state.
But when we'll
But when
talk
we'll
about
talk
the
about the
surface
surface
atoms,
atoms,
then what will
then what will
happen?
happen?
At the
At the
surface
surface
atoms, there
atoms,
are no
there are no
neighbors
neighbors
on their.
on their.
So if
So
it is
if
the
it is the
surface
surface
atom,
atom,
it is
it
not
is not
bonded
bonded
completely,
completely,
and these are
and these
called
are
the
called the
dangling
dangling
bonds. So
bonds.
when
So
we are
when we are
moving
moving
uh,
uh,
from the
from the
bulk to
bulk to
surface,
surface,
it
it
increases
increases
the
the
number of
number of
dangling
dangling
bonds,
bonds,
which
which
creates a
creates
high
a high
potential
potential
energy.
energy
That is
that is
called the
called the
surface free
surface free
energy, and
energy.
that's
And
why
that's why it,
when we were
when we are
saying that
saying that
if we are
if we are
moving from
moving from
the
the
bulk to
bulk to
nano,
nano,
uh, it makes
it
the
makes the
surface
surface
atoms
atoms
highly
highly
reactive.
reactive.
So that's
So that's
why
why
in
in
hydrogen fuel
hydrogen fuel
cells we
cells we
use
use
the
the
platinum
platinum
powder.
powder.
So which
So
is
which is
like
like
nanoscale
nanoscale
platinum
platinum
powder,
powder,
because
because
if we
if
will
we will
use the
use the
bulk
bulk
platinum,
platinum,
it
it
has a
has a
negligible
negligible
fraction of
fraction of
exposed
exposed
surface
surface
atoms.
atoms.
So
So
that will
that will
make
make
uh,
uh,
platinum
platinum
bulk
bulk
highly
highly
unreactive.
unreactive.
But
But
nanoscale
nanoscale
platinum
platinum
powder
powder
has
has
nearly all
nearly all
its
its
atoms
atoms
exposed at the
exposed at the
surface with
surface with
higher
higher
surface
surface
energy,
energy,
and that
and
will
that will
increase the
increase the
active
active
reaction
reaction
sites,
sites,
so that
so
we
that
can
we can
facilitate the
facilitate the
chemical
chemical
reaction. So
reaction. So
that's why
that's
we
why
are
we are
using
using
these
these
powders in
powders in
hydrogen
hydrogen
fuel
fuel
cells.
cells.
So
So
the
the
other
other
part
part
is,
is,
so
so
like
like
we are
we are
seeing
seeing
that the
that the
melting
melting
properties.
properties.
So
So how the
what is
what
the
is the
change in
change in
melting
melting
property?
property?
So
So
nanoparticles
nanoparticles
melted
melted
significantly lower
significantly lower
temperature than
temperature
their
than their
bulk
bulk
counterparts.
counterparts.
So what is
So
the reason
what
of
is the
that? The
reason of
same
that? The
reason.
same reason.
The
The
surface
surface
atoms have
atoms have
fewer neighboring
fewer neighboring
bonds
bonds,
holding them in
holding
the
them in
crystal
the
lattice,
crystal lattice,
since
since
less thermal
less
energy
thermal
is
energy is
required to break
required to
these
break
surface
these
bonds,
surface
and
bonds, and
we can
we
trigger
can
any
trigger
phase
any phase
transition.
transition.
So
So, and
nanoparticles
nanoparticles
melt at the
melt at the
reduced
reduced
temperatures.
temperatures.
Suppose
Suppose
if we have
if
the
we have
bulk
the
gold,
bulk gold,
it
it
need
need
very high
very high
temperature, greater
temperature,
than
greater than
1000 degrees
1000
Celsius.
degrees Celsius.
Approximately,
Approximately,
bulk gold
bulk gold
melts at
melts at
1064 degrees
1064 degrees
Celsius. But if
Celsius.
we
But
have
if
a
we
2
have a 2
nanometer gold
nanometer gold
nanoparticle, it will
nanoparticle,
melt
it
near
will melt
300
near
degrees
300
Celsius.
degrees Celsius.
So
So
you can
you
see
can
the
see the
different chemical
different chemical
properties, like this
properties, like this
mechanical,
mechanical,
thermal,
thermal,
melting,
melting,
electrical
electrical
properties. We
properties.
will
We
see
will
one by
see
one
one by
depending
one
upon
depending
the
upon the
application.
application.
So
So
first we
first
saw the
we saw
higher
the higher
surface to
surface
volume
to volume
ratio,
ratio,
so which is
so which
showing
is
the
showing the
3 by
3
r
by r
factor. If the
factor. If
size
the
will
size
be
will be
less,
less,
surface to
surface
volume
to volume
ratio will
ratio will
increase,
increase,
and
and
it
fundamentally
fundamentally
it will
affect the
affect the
physical and
physical and
chemical
chemical
properties.
properties.
So
So,
and it
and
will
it will
increase
increase
the
the
catalytic
catalytic
efficiency and
efficiency
the
and the
absorption
absorption
capacity,
capacity,
based on
based
the
on the
same
same
explanation,
explanation,
that at
that
the
at the
surface
surface
the
the
bonds are
bonds are
unfulfilled, and
unfulfilled, and then
we
they will
make the
make the
dangling,
dangling, they will
make the
make the
dangling
dangling
bonds.
bonds. So,
For
for
example,
example,
platinum
platinum
nanoparticles we are
nanoparticles we are
using
using
in the
in the
fuel
fuel
cells.
cells.
In
In
biomedical
biomedical
application
application
also, the
also, the
large
large
surface
surface area we will have,
we can
we can
efficiently
efficiently
carry and
carry and
release
release
drugs
drugs
at
at a
specific.
specific size.
Now,
Now,
what are the
what are the
quantum
quantum
effects
effects
in the
in the
size
size
dependent
dependent
properties?
properties?
So,
So,
first of
first of
all,
all,
mm,
mm,
so
so
when the
when the
materials have
materials are
reduced
reduced,
the
the
nanoparticles,
nanoparticles,
quantum
quantum
mechanical
mechanical
effects
effects
become
become
prominent,
prominent,
resulting in
resulting
the
in the
size
size
dependent
dependent
properties.
properties.
So, what
So,
is
what is
actually
actually
happening?
happening?
So,
So,
what is
what
meant
is
by
meant by
quantum
quantum
confinement?
confinement?
Where we
Where we are
dealing the
dealing the
electrons
electrons
are
are
restricted to
restricted
very
to very
small
small
volume.
volume.
What will
What will
happen?
happen?
It will
It
lead
will
to
lead us
the
to the
discrete
discrete
energy
energy
levels
levels
rather than
rather
the
than the
continuous
continuous
bands in
bands
bulk.
in bulk.
So,
So,
if we are
if we are
dealing with
dealing
the
with the
discrete
discrete
energy
energy
levels,
levels,
uh,
uh,
it will
it will
affect
affect
the
the
electrical,
electrical,
optical,
optical,
and the
and the
magnetic
magnetic
properties.
properties.
So,
So,
for
for
example, we
example, we
discussed the
discussed the
quantum
quantum
dots.
dots.
We
We
can
can
tune
tune
the
the
PL
PL
emission
emission
by
by
changing the
changing the
particle
particle
size,
size,
and it
and
will
it will
also
also
change
change
the,
the,
like,
like,
obviously
obviously
whatever the
whatever the
emission
emission
happens,
happens,
depending
depending
upon the
upon the
emission
emission
wavelength, the
wavelength,
color
the
will
color will
automatically change.
automatically change.
That
That
is
is
called
called like
PL.
PL.
And the
And the
other
other
application of
application of
quantum
quantum
effects we can
effects we
see
can
in
see
the
in the
super
super
paramagnetism
paramagnetism
in iron
in iron
oxide
oxide
nanoparticles.
nanoparticles.
So
So
in that
in
case,
that
in
case, so in
general,
general,
when we deal
when we
with
deal
the
with
magnetic
magnetic
particles,
particles,
paramagnetism,
ferromagnetism, and
perimagnetism, it
perimagnetism, it
forms a
forms a
hysteresis loop.
hysteresis loop.
But in
But
super
in super
paramagnetism,
paramagnetism,
it is not
it
like
is not
that.
like that.
We see the
We'll see
reason
the
in the
reason in
further
the
classes,
further
but
classes,
these
but
are
is
general
the general
examples.
examples,
Like when
like
we are
when we are
moving from
moving
bulk to
from bulk
nano,
to
what
nano,
is
what is
in
in
which
which
phase,
phase,
which
which
properties we
properties
can
we
see
can
the
see the
changes.
changes.
So,
So,
uh,
um,
on the
on the
basis of
basis of
this
this
quantum,
quantum,
so we
so
all
we all
have
have
dealt with
dealt with
this
this
particle in a
particle in a
1D
1D
box.
box.
So in
So in
that
that
also we
also
can
we
see
can
that
see that
how does
how does
the
the
quantum
quantum
particle in a
particle in
1D
a 1D
box
box
explain the
explain the
quantization in
quantization in
nanoparticles.
nanoparticles.
So
So
at there
at
we were
there we were
considering a box
considering a
of
box
length
of
L.
length L.
Energy levels
Energy
are
levels
given
are
by
given by
n is
n
equals
is
to
equals
n
to
square h
n
square
square h
upon
square upon
8 mm
8
square
mm
if we are
square if
talking
we are
about
talking about
E.
E.
So
So
boundary
boundary
dimension when the
dimension when
length
the
will
length will
increase
increase
as the boundary
as the boundary
dimension
dimension
L.
L.
If it will
If it will
shrink to the
shrink to the
nanoscale,
nanoscale,
energy
energy
levels will
levels
become
will become
quantized
quantized,
and it
and
will
it will
convert from
convert
the
from the
continuous band
continuous
to the
band to the
discrete bands.
discrete bands.
So
So
now,
now,
when
when
uh,
uh,
the
the
nanoparticle
nanoparticle
size is
size is
shrinking,
shrinking,
how it is
how it is
affecting its
affecting its
band gap
band gap
and
and
optical emission.
optical emission.
So when the
So when the
particle size
particle size is
decreases,
decreases,
it means
it means
quantum
quantum
confinement
confinement
will
will
push the
push the
energy levels
energy levels
apart.
apart.
It means
It means
what is
what
happening?
is happening?
If energy
If energy
levels
levels
will
will
be far
be
away,
far away,
it means
it
it is
means it is
increasing the
increasing the
semiconductor band
semiconductor
gap.
band gap.
Since
Since
the
the
energy levels
energy
are
levels are
changing, so band
changing, so
gap will
band gap will
increase,
increase,
and this
and
wider
this wider
band gap
band gap
will require
will
the
require the
higher
higher
energy for
energy
the
for the
excitation.
excitation.
So
So
now
now
it will
it will
emit a
emit a
different
different
wavelength
wavelength
upon
upon
recombination. So how
recombination.
is
So how is
PL
PL
happening?
happening?
One,
One,
we will
we will
excite some
excite some
electrons
electrons
from
from
valence band
valence
to
band to
conduction band.
conduction band.
Then upon
Then upon
when it will
when
move
it will
from
move
the
from the
highest
highest
excited state to
excited
ground
state to
state, it will
ground state, it will
recombine and will
recombine
give
and
us
will
a
give us
photon.
a photon.
It will be
It
have
will be
some
have some
energy. So
energy. So
depending upon
depending
the
upon
band
the
gap,
band
the
gap, the
energy will
energy
change.
will change.
So that's
So
why
that's why
depending upon the
depending upon
size
the
of
size of
particle,
particle,
we will
we
get the
will get the
different
different
wavelength.
wavelengths.
So
So
so in
so in
how
how
the
the
density of
density of
states
states
changes.
changes.
So
So
in
in
the
the
3D,
3D,
2D,
2D,
1D, and
1D, and
0D.
0D.
So when
So
we are
when we are
talking
talking
about
about
3D,
3D,
it is
It is
proportional,
proportional.
the
The
density of
density
state
of
is
state is
proportional to the
proportional to the
square root
square
of
root of
E.
E.
Then
When we
talk about
talk about
2D.
2D, so
You
you
have
have
studied
studied
this
the
Hall
this Hall
effect, in
effect.
this you
In this
get
you
the
get
step
the step
function.
function.
And when
And
you
when
deal
we
with
deal with
the
the
1D
1D
quantum
quantum
wire,
wire,
density of
density of
states will be
states will be
proportional to
proportional to
E
E
to
की
power
power
minus
minus
half.
half.
And for
And for
the
the
0D, we
0D,
will
we will
get
get a
a Dirac
Dirac
delta
delta
function.
function.
So
So
next is
next is
this.
this.
So these
So
are
these
the
are the
basic
basic
properties
properties
when we are
when we are
moving
moving
from
from
bulk to
bulk to
nano.
nano, and
How,
how,
like
like
physically, what
physically,
is
what is
happening?
happening.
If
If
it
it
is the
is the
color is
color is
changing,
changing,
how it is
how it is
happening?
happening,
Because the
because the
band gap
band
is
gap is
changing.
changing.
Nanoparticles are
Nanoparticles are
becoming
becoming
reactive.
reactive.
Why are
Why
they
are they
reactive?
reactive?
Because
Because
more
more
dangling
dangling
bonds are
bonds are
there.
there.
So
So
for a
for a
particular
particular
change
change
in
in
property,
property,
there are
there are
reasons
reasons
behind that.
behind that.
So
So
can
can
someone
someone
tell the
tell the
four
four
uh,
uh,
fundamental
fundamental
principles of
principles of
quantum
quantum
confinement in
confinement in
nanomaterials?
nanomaterials?
Just like I
Just like I
told.
told.
Okay,
Okay,
so
so
four
four
things.
things.
First of
First of
all,
all,
what is
what is
from
from
where we
where
are
we are
defining
defining
the
the
threshold
threshold
for
for
like
like
quantum
quantum
confinement will
confinement will
start. So
start.
this
So
is
this is
defined by
defined
the
by the
Bohr
Bohr
exciton
exciton
radius.
radius.
Second thing
Second thing
is
is
continuous
continuous
energy
energy
bands
bands
are
are
changing
changing
into
into
discrete
discrete
states.
states.
Third
Third
is
is
band gap
band
is
gap is
increasing
increasing
as
as
particle
particle
size
size
is
is
shrinking.
shrinking.
Fourth
Fourth
is
is
optical
optical
absorption.
absorption.
We can
We can
tune by
tune via
particle
particle
dimensions.
dimensions.
So
So
these are
these
the
are the
things.
things.
So
So
next we
next
are
we are
uh,
uh,
moving
moving
to the
to the
Moore's law.
Moore's law.
Moore's
Moore's
law,
law,
what is
what is
this?
this?
Like we
Like
are
we are
observing that
observing
the
that the
number of
number of
transistors
transistors
on a
on a
microchip
microchip
is
is
getting
getting
doubled
doubled
approximately every
approximately
2
every two
years,
years,
but the
but the
cost
cost
is
is
halved.
halved.
Basically,
Basically,
transistor
transistor
density is
density is
increasing
increasing
because we
because
are
we are
reducing the
reducing the
size,
size,
and
and
it is
it is
leading to an
leading to an
exponential
exponential
growth
growth
in
in
computing
computing
power.
power.
But
But
the
the
major
major
limitations of
limitations of
Moore's law
Moore's
is
law is
heat
heat
dissipation.
dissipation.
So if
So
the
if the
number of
number of
transistors are
transistors are
increasing,
increasing,
obviously
obviously
there will
there
be
will be
more
more
heat
heat
dissipation,
dissipation,
and
and
lithography
lithography
limits
limits
also
also,
since it
since
is
it is
reaching to
reaching 2
nanometers.
nanometers.
So
So
that's
that's
why
why
we
we
move
moved
from
from
like what
like what
this
this thing.
we will
We will
talk
talk
about the
about the
impact
impact
of
of
nanotechnology.
nanotechnology.
Next
Next
is,
is,
so
so
then we
then we
started with
started
the
with the
miniaturization of
miniaturization
the
of the
devices.
devices.
So
So
traditional, as
traditional, as it
as I showed
as
you
I
the
showed
full
you the
screen in
first
the
screen
past,
in the
when we
past,
were
when we're
dealing with the
dealing with the
traditional
traditional
silicon-based
silicon based
devices,
devices,
uh,
uh,
this
this
we were
we were
approaching the
approaching the
physical and
physical
quantum
and quantum
mechanical limits
mechanical
at
limits at sub
sub-nanometer
nanometer
scales.
scales.
So
So
nanomaterials provide
nanomaterials provide
pathways to
pathways to
continue
continue
Moore's law,
Moore's law,
and
and
where
where
nano-electromechanical
nano-electromechanical
systems
systems
utilize
utilize
nanomaterials to
nanomaterials
create
to create
highly
highly
sensitive
sensitive
sensors.
sensors.
So as
So
the
as the
silicon
silicon
channels
channels
shrink below
shrink
2
below 2
nanometers,
nanometers,
quantum
quantum
tunneling or
tunneling
severe
or
electron
severe
decay
electron
through
decay
closed
through closed
gates,
gates,
it will
it
generate
will
the
generate
excess
the
heat,
excess heat,
so that
so that
1D
1T carbon
carbon nanotube and 2D
nanotube and 2D
graphene
graphenes
are
are
substituted for
substituted
the
for the
silicon due to
silicon
their
due to their
atomic
atomic
thickness, high
thickness,
carrier
high carrier
mobility,
mobility,
and
and
superior
superior
electrostatic gate
electrostatic
control.
gate control.
So
So
these are the
these are the
things,
things
like
like
we are.
we are.
So first
So
we
first we
dealt with
dealt
silicon.
with
Okay,
silicon.
now
Okay,
we
now
can't go
we
beyond
can't
2
go beyond 2
nanometers. So
nanometers.
we
So
are
we are
looking for
looking
the
for the
materials which has
materials which
better
has better
properties as
properties as
compared to
compared to
silicon.
silicon.
The next
The
thing
next
is
thing is,
how do
how do
uh,
uh,
gate
gate
all around
all around
transistor
transistor
architectures
architectures
prevent
prevent
quantum
quantum
tunneling
tunneling
leakage.
leakage.
So what it
So
is
what it
doing
is
is
doing
we
this,
are
we are
making the
making the
structure
structures with
vertically stacked
vertically stacked
line
line
like this,
like this,
vertically
vertically
stacked
stacked
semiconductor
semiconductor
nanowires,
nanowires,
nanosheets, and
nanosheets,
we are using
and we are
ALD
using
process
ALD
for the
process for
stacking.
the stacking.
ALD
ALD
is
is
atomic layer
atomic layer
deposition, where
deposition,
the
where the
layer is
layer is
depositing layer
depositing
by
layer
layer,
by layer,
and the
and the
conductive gate
conductive gate
material
material
surrounds the channel
channel
on
on
all
all
the
the
four
four
sides,
sides,
but
but
that will
that will
control
control
the
the
electrostatic
electrostatic
control, and it
control, and
will
it will
suppress the
suppress
leakage
the
at the
leakage at
atomic.
the atomic limit.
Oh,
Oh,
and
and
next is,
next
if
is
we are
if we are
reducing the
reducing the
size
size
which we are
which we are
achieving with the
achieving with the
nanomaterials,
nanomaterials,
it will
it
help
will help
the
the
faster data
faster data
processing
processing
and
and
storage.
storage.
Also, along
Also,
with
along
that,
with that, it will
it
uh,
reduce the
reduce the
cost
cost
and the
and the
material
material
consumption
consumption
also.
also.
So,
So,
next is,
is
yeah.
yeah.
So here
So
is,
here is
we will
we will
see
see
the
the what are the advantages and disadvantages
if we
if
are
we are
reducing the
reducing
size,
the
if we
size,
are
if we
doing
are
the
doing the
miniaturization of
miniaturization
the
of the
devices.
devices.
So
So
first is
first is
size and
size and
portability.
portability.
So
So
obviously,
obviously
size it's
size is
smaller,
smaller, it will
be light
be lightweight
and
and
compact
compact
device we
device
can
we can
make.
make.
But
But
obviously,
obviously
when
when
we
we
are
are
dealing with
dealing with
such
such
chips,
chips,
nanoscale
nanoscale
chips, it
chips,
is
it
very
is very
difficult to
difficult to
handle,
handle,
and we
and we
need
need
uh,
uh,
advanced
advanced
technologies like
technologies like
electron beam
electron beam
lithography to
lithography to
manipulate
manipulate
at the
at the
nanoscale.
nanoscale.
Performance
Performance
wise,
wise,
it is
it is
higher speed.
higher,
It has
it
higher
has
speed due
higher
to
speed due to
short electron
short
path.
electron path.
But then,
But then
this when the
this
size
when
is
the size is
decreasing,
decreasing,
heat
heat
dissipation
dissipations
increases at a
increases
smaller
at a
scale.
smaller scale.
So
So
there are
there are
advantages also
advantages
and
also and
disadvantages also.
disadvantages also.
Depending upon
Depending
the
upon the
application, we are
application, we
dealing
are
with the
dealing with the
sizes
sizes
and we are
and
tuning
we are
the
tuning the
materials.
materials.
So
So
in
in
power
power
consumption
consumption
also, in
also, in
using
using
nanomaterials,
nanomaterials,
the power
the power
usage
usage
is
is
low,
low.
but there is
There is
tunneling effect
tunneling effect
where there
where
is
there
leakage
is
of
leakage of
current due to
current due to
quantum
quantum
tunneling.
tunneling.
In terms
In
of
terms of
material
material
uses,
uses,
less raw
less raw
material
material
used,
used,
and
and
but the
but the
fabrication
fabrication
defects can
defects
have
can
greater
have greater
impact. Okay,
impact.
so this
Okay,
is
so
very
this is very
important point
important point that
we are
when we are
choosing
choosing when we are
the
dealing with the
nanomaterials.
nanomaterials,
It is
it
very
is very
difficult to
difficult to
fabricate
fabricate
with a
with a
smaller
smaller
feature
feature
size.
size.
And then
And
new
then new
functionalities. Okay,
functionalities.
so
Okay, so
super
super
paramagnetism
paramagnetism
and
and
spintronics,
spintronics,
quantum
quantum
dots. We
dots.
can
We
tune
can
the
tune the
PL.
PL.
These are
These
all
are all
effects
effects
like
like
that were
that were
not
not
allowed in
allowed in
case of
case
bulk
of bulk
materials, but
materials,
we
but
can
we can
easily do
easily do
this
this
using
using
by
by
tuning the
tuning the
size of
size
the
of the
quantum
quantum
dots.
dots.
But
But
sometimes,
sometimes,
suppose you
suppose
are
you are
fabricating the
fabricating the
gold
gold
or
or
silver
silver
nanoparticles,
nanoparticles,
but
but
the
the
size is
size is
different.
different. Like
Suppose you
suppose
want
you want
10
10
nanometer
nanometer
size
size
or
or
20,
20
50
50
nanometer
nanometer
size,
size,
but
but
during
during
fabrication,
fabrication,
it
it
is
is
made up
made
of
up of
some
some
different
different
color
color.
with
It's
different
different
size.
size.
So
So
obviously the
obviously the
PL will
PL
be
will
of
be of
different,
different,
emission will
emission
be
will
of
be of
different
different
wavelength.
wavelength.
So
But
sometimes
sometimes
also
also
quantum
quantum
effects
effects
are
are
unpredictable.
unpredictable.
Then you
Then
can
you
add
can add
on the
on the
basis of
basis of
economic
economic
impact, it
impact, it
drives
drives
consumer
consumer
electronic
electronic
wearables,
wearables,
medical
medical
devices,
devices,
and
and
it
it
needs
needs
extremely
extremely
high
R&D and
manufacturing
manufacturing
costs.
costs.
In
In
biomedical
biomedical
application, we
application,
can
we
do the
can do the
targeted
targeted
drug
drug
delivery
delivery
and
and
diagnostic tools
diagnostic
at
tools at
cellular
cellular
level.
level.
Potential
Potential
toxicity or
toxicity or
long
on
term,
long term,
obviously,
obviously,
there can
there
be,
can be
because of
because of
these
these
materials, it
materials, it
can
can
be
be
long
long
term
term
health
health
effects
effects
that we
that
have
we
to
have to
consider.
consider.
On a
On a
sustainability
sustainability
level,
level,
e-waste
e-waste
definitely it
definitely
will
it will
reduce,
reduce,
and we
and
will use
we will
the
use the
biodegradable
biodegradable
materials.
materials.
But
But
recycling can
recycling
be
can be
challenging.
challenging.
So
So
then what
then what
about the
about the
mechanical
mechanical
properties of
properties of
these
these
nanomaterials?
nanomaterials?
So we
So
saw
we
that.
saw that.
So
So
there is
there
one
is one
effect
effect
that
that
deals with
deals with
the
the
mechanical
mechanical
strength
strength
compared to the
compared to the
bulk
bulk
counterpart. That
counterpart,
is
that is
Hall
Hall
patch
patch
effect.
effect.
What it
What it
what
what
does it
does it
say?
say?
It
It
says it's
says
a
it's a
phenomenon
phenomena
where
where
decreasing the
decreasing the
size of
size of
grain
grain
size of
size of
polycrystalline
polycrystalline
material,
material,
it will
it will
increase
increase
to
to
it will
it will
increase
increase
its
its
yield
yield
strength.
strength.
So
So
whenever the
whenever the
grain
grain
size will
size will
decrease
decrease
to
to
nanoscale,
nanoscale,
the
the
number of
number of
grain
grain
boundaries
boundaries
increases.
increases.
So when
So
the
when the
grain
grain
boundaries will
boundaries will
increase,
increase,
it
it
will
will
block
block
the
the
dislocation
dislocation
motion.
motion.
There are
There
many
are
grain
many grain
boundaries,
boundaries,
and now
and
the
now the
motion is
motion is
prohibited.
prohibited,
So it
so
will
it will
automatically
automatically
strengthen the
strengthen
material.
the material.
So
So
the
the
relationship is
relationship
Hall
is
price
Hall price
relationship.
relationship
Sigma
is
y is
sigma y
equals
is
to
equals to
sigma
sigma
I
I
plus
plus
KD one
KD
half.
one half.
So sigma y
So
is the
sigma y is
yield
the
strength,
yield strength,
sigma is the
sigma is the
friction
friction
strength,
strength,
stress K is
stress
equals
K
to
is equals to
strengthening
strengthening
coefficient, and D is
coefficient, and
equals
D
to
is
grain
equals to
size.
grain size.
So you can
So
see
you
in
can
this
see in
plot
this
that
plot that
as the
as the
grain size
grain size is
approximately 10
approximately 10
nanometer,
nanometer,
then
then
when there
when
is a
there is a
decrease in
decrease
grain
in grain
size,
size,
the
the
yield
yield
strength is
strength is
increasing.
increasing.
So these
So
are
these
the
are the nano diamond, nano
nanocrystalline and
crystalline, and
nano
nano
composite
composite
material
material
exhibit
exhibit
high
high
hardness.
hardness.
For
For
example,
example,
nano
nano
diamond tips
diamond tips
and
and
titanium
titanium
nitride
nitride
nanoparticles.
nanoparticles.
Yeah.
Yeah.
So the
So the
next
next
thing
thing
is
is
improved
improved
electrical
electrical
conductivity.
conductivity.
So
So
why the
why the
electrical
electrical
conductivity is
conductivity is
getting
getting
improved?
improved?
Electrical
Electrical
conductivity is
conductivity is
improved
improving
due
due to
to reduced
reduced
scattering of
scattering of
electrons,
electrons,
enhanced
enhanced
mobility.
mobility.
So, for
So, for
example,
example, in
graphene.
graphene,
So,
so
graphene
graphene
is a
is a
2D
2D
material.
material.
It
It
exhibits
exhibits
electrical exceptional
exceptional
electrical
electrical
conductivity
conductivity
even
even
greater than
greater than
copper.
copper.
It's
It's
thin,
thin,
it's
it's
lighter.
lighter.
Similarly,
Similarly,
carbon
carbon
nanotubes,
nanotubes,
it
it
provides the
provides the
minimal
minimal
resistance,
resistance,
and
and
without
without
scattering,
scattering,
a
a
long
long
distance
distance
can be
can be
traveled over
traveled
a
over a
micrometer
micrometer
range.
range.
So,
So,
high
high
conductivity
conductivity
will
will
enable the
enable the
faster
faster
electronic
electronic
devices,
devices,
more
more
efficient
efficient
energy
energy
storage
storage
system,
system,
and
and
transparent
transparent
conductive
conductive
films
films
for
for
flexible
flexible
electronics.
electronics.
Then
Then
silver
silver
nanowires
nanowires
are
are
used to
used to
create
create
flexible
flexible
touch
touch
screens
screens
and
and
organic
organic
LEDs.
LEDs.
Now,
Now, why
how
how
the
the
optical
optical
properties
properties
are
are
getting
getting
better
better
in
in
case
case
of
of
nanomaterials?
nanomaterials?
So,
So
when we
when we
talk
talk
about
about
the
the
surface
surface
properties,
properties,
there is
there is
one
one
physical
physical
phenomenon
phenomenon
that
that
happens
happens
at a
at a
surface level,
surface
that
level,
is
that is
LSPR.
LSPR.
What is
What is
LSPR?
LSPR?
LSPR
LSPR
is
is
a
a
localized
localized
surface
surface
plasmon
plasmon
resonance.
resonance.
So
So
first of
first
all,
of
there
all,
is
there
a
is a
plasmon.
plasmon.
So
So
it
it
is
is
a
a
quasi
quasi
particle,
particle,
and
and
if
if
the
the
thickness
thickness
of
of
the
the
film is
film is
at the
at the
nanoscale,
nanoscale,
then
then
there
there
it
it
affects
affects
surface
surface
effect.
effect.
Localized
Localized
because
because
we saw
we
that
saw
at
that at a
nanoscale
nanoscale
level,
level,
electronic
electronic
movement
movement
is
is
dislocation
dislocation
decreases. So
decreases.
that's
So
why
that's why
we are
we are
saying
saying
the
the
localized.
localized.
So it
So
is
it is
LSPR is
LSPR
the
is the
resonant
resonant
oscillation
oscillation
of the
of the
conduction band
conduction band
electrons in a
electrons in a
metallic
metallic
nanoparticle
nanoparticle
confined to the
confined to the
nanoparticle
nanoparticle
surface under
surface under
excitation of
excitation
light.
of light.
So
So
you can
you
see
can see the
this
this
light
light
wave,
wave
electron
electron
cloud is
cloud
there.
is
So
there. So
this will
this will
when the
when
light
the
will
light will
fall,
fall,
there will be
there will be
formation of
formation of
positive and negative charge
positive and
dipole
negative
moment,
charge dipole
and
moment,
then
and
it
then it
will
will
be
be
produce the
produce the
oscillation which we are
oscillation which we are
considering as
considering
resonant
as resonant
oscillation,
oscillation,
and you can see
and
the
you can see
electric
the
field is
electric field is
continuously
continuously
resonating.
resonating.
And why is
And
it
why is it
localized? Because
localized?
the
Because the
electromagnetic
electromagnetic
field
field
is
is
confined to a very
confined to a very
small
small
volume,
volume,
unlike
unlike
propagating
propagating
surface
surface
plasmons on thin
plasmons on
films.
thin films.
So because
So
of
because of
that
that
phenomena,
phenomena,
LSPR
LSPR
and
and
quantum
quantum
confinement
confinement
effects,
effects,
there is
there
a
is a
superiority in the
superiority in the
optical
optical
properties.
properties.
And
And
when it
it
occurs
occurs
when the
when the
frequency of
frequency of
incident
incident
photons matches
photons
the
matches the
natural
natural
frequency of
frequency of
surface
surface
electrons,
electrons,
which are at
which
the
are at the
surface
surface
of our,
of our,
which are at the
which are at the
surface,
surface,
and
and
when the
when the
frequency of the
frequency of the
incident
incident
photon
photon
will match
will
the
match the
natural
natural
frequency of
frequency
surface
of surface
electrons
electrons
oscillating against
oscillating
the
against the
restoring force of
restoring force of
positive
positive
nuclei.
nuclei.
So
So
in
in
LSPL, these are the
LSPL, these
silver
are the silver
nanoparticles. You can
nanoparticles.
see
You can see
they are of
they are of
various
various
sizes,
different
and
sizes and
different
different
colors
colors
also.
also.
So
So
the
the
conduction
conduction
electrons will
electrons will
oscillate
oscillate
collectively in
collectively in
response to the
response to the
incident
incident
electric field,
electric field,
and at a
and at a
particular
particular
frequency
frequency
that is
that
known
is
as the
known as the
LSPL
LSPR
frequency, the
frequency, the
oscillation
oscillation
becomes
becomes
resonant. So
resonant.
what
So
it will
what it
give?
will
It
give?
will
It
give
will
us
give
through the
us through the
strong
strong
absorption,
absorption,
scattering,
scattering,
and
and
electric field,
electric field,
local
local
electromagnetic
electromagnetic
field
field
enhancement.
enhancement.
So what
So
are the
what are
key
the key
features of
features of
LSPR is?
LSPR is
Feature is
feature is
strong light
strong light
absorption.
absorption.
And what
And what
will be
will
the
be the
effect
effect
of
of
strong light
strong light
absorption?
absorption?
It will
It will
change the
change the
color.
color.
So
So
absorption
absorption
is
is
based
based
on the
on the
change in the
change in the
band.
band gap.
So that
So
will
that will
automatically
automatically
change the
change the
color
color
tuning and
tuning and
solution.
solution.
Enhancement of
Enhancement of
local
local
electric
electric
field.
field.
So
So
you
you
can
can
show
show
the
the
10 to
10 to
100
100
times
times
amplification
amplification
at the
at the
surface.
surface.
Then
Then
sensitivity, so
sensitivity,
we
so
are
we are using
making the
making the
highly
highly
ultra
ultra
sensitive
sensitive
sensor,
sensors,
and high
and high
sensitivity to
sensitivity to
environment is the
environment is the
basis of
basis
this
of this
biosensor.
biosensors.
So we are
So we are
dealing
dealing
with
with
the
the
nanomaterials for
nanomaterials for
making
making
these
these
highly
highly
sensitive
sensitive
sensors.
sensors.
Then
Then
size and
size
shape
and shape
dependent.
dependent.
So
So it
we
is
can
we can
tune
tune
depending
depending
upon the
upon the
size and the
size and
shape.
the
We
shape.
can
We
tune
can tune
across
across
from
from
visible to
visible to
NIR
NIR
region.
region.
So you
So
can
you
see
can
that
see
if
that
we
if we
have the
have the
whole
whole
nanoparticles
nanoparticles
and the
and the
size is
size is
between 10
between
to
10 to
20
20
nanometer, it will
nanometer, it
give
will
us the
give us
red
the red
color.
color.
These are
These
the
are
PL.
the PL.
So
So depending upon,
so
so
we will
we will
excite
excite
these
these
nanoparticles with some
nanoparticles with some
excitation wavelength,
excitation
suppose
wavelength, suppose
green wave,
green wave,
green light
green light
530. If
530.
we are
If we are
using
using
laser,
laser,
then the
then the
emission will be
emission
at
will be
some
at the
different
some
wavelength.
different
So
wavelength. So
you can
you
see
can
the
see
band
the band
structures are
structures
changing.
are changing.
So band
So band
structure, the
structure,
band
the
gap is
band gap is
changing
changing
depending upon
depending
the change
upon the
in
change
band
in
gap.
band gap.
The
The
recombination energy
recombination energy
changes,
changes,
absorption
absorption
changes. That's
changes.
why
That's
we
why
are
that we
seeing
are
the
seeing
different
the
colors.
different color.
So the
So
10
the
to
10
20
to 20
nanometer
nanometer
size,
size,
red
red
band gap.
band gap,
2 to
2 to
5
5
yellow.
yellow,
Greater than
greater than
20, it is
20, it
giving
is
us
giving us
purple color.
purple color.
Similarly, for
Similarly, for
silver
silver
nanoparticles,
nanoparticles,
this
this
the
the
size is
size is
different, the
different,
color
the
is
color is
different. That
different.
is
That is
40
40
nanometer, it
nanometer,
is
it is
giving us
giving a
blue
blue
color,
color,
100
100
nanometer, it
nanometer,
is
it is
giving us
giving us
yellow
yellow
color,
color,
and the
and the
shape is
shape is
also
also
different.
different.
So
So
next
next
is,
is,
so we
so we
saw
saw
the
the
electronic
electronic
properties,
properties,
optical
optical
properties,
properties,
mechanical
mechanical
properties, all are
properties,
getting
all are getting
enhanced. Now
enhanced.
how
Now how
the
the
magnetic
magnetic
properties is
properties
getting.
is getting improved.
So
So
there is one
there is
phenomenon
one
called
phenomena
super
called super
paramagnetism,
paramagnetism,
which is a
which is a
magnetic
magnetic
behavior
behavior exhibited by ferromagnetic or
ferromagnetic
ferrimagnetic
nanoparticles,
nanoparticles,
where thermal
where
energy is
thermal energy is
sufficient to
sufficient to
randomize the
randomize
direction
the
of
direction of
magnetization over
magnetization
time.
over time.
So
So
despite having
despite
strong
having
magnetic
strong
moments
magnetic
like
moments like
ferromagnet,
ferromagnets,
these
these
particles do
particles
not
do
retain
not retain
magnetization in the
magnetization in the
absence of
absence of
external
external
magnetic field.
magnetic field.
So just
So
like it is
just like it
not
is not
forming any
forming any
hysteresis loop,
hysteresis loop,
like
like
in
in
hysteresis loop
hysteresis
we
loop
were
we were
having
having
non-zero
non-zero
causivity
causivity
and
and
remanence,
remanence, but
in
here
case of
in
this
case of this
phenomena
phenomena
we are
we
having
are
this,
having this,
we are not
we are
having
not
that
having that
what we say
what we say
hysteresis loop.
hysteresis
It
loop.
is
It
some
is
of
some
different
of
shape
different
which
shape
I will
which
show
I will
in this
show in
slide.
this slide.
So what is the
So what is the
origin of
origin
that
of
super
that super
paramagnetism?
paramagnetism?
So
So
in
in
small
small
nanoparticles
nanoparticles
lesser
lesser
than
than
20
20
nanometer,
nanometer.
so
So
these are the
these
grain
are the
boundaries.
grain
You can
boundaries. You
see
can
that
see that
these are
these
dominant
are
walls
domain walls
basically when we are
basically when we
talking
are
about
talking about the
the magnetic
magnetic
nanoparticles.
nanoparticles.
So
So
when the
when
size
the
is
size is
lesser than
lesser
20
than 20
nanometer,
nanometer,
the
the
entire
entire
particle will
particle
become a
will become
single
a single
magnetic domain.
magnetic domain.
There will be
There
no
will be no
dominant walls.
domain walls.
So the
So the
magnetic
magnetic
moment of
moment
the
of the
entire
entire
particle will
particle will
behave like
behave
a
like a
giant spin.
giant spin.
So
So thermal,
whenever
whenever
there
there
will
will
be
be
some
some
thermal
thermal
fluctuations,
fluctuations,
it
it
will
will
flip
flip
the
the
direction
direction
of
of
the
the
entire
entire
magnetic
magnetic
moment.
moment.
That will lead
That will
to
lead to the
the zero time
zero
average
time
zero
average zero
magnetization.
magnetization.
So this is
So
the
this is
MH
the
curve for
MH curve for
superparamagnetism. So you can
superparamagnetism. So
see
you
that
can
this
see that
is
this is
the curve with
the curve with
S shape, that
S
is
shape, that is
sigmoidal.
sigmoidal. and it is symmetric about the origin.
Wherever
Wherever you can see for the ferromagnetism,
it is not
it is not like this. It is
as
as a
it has
it
some
has some
magnetic field
magnetic field
for the
for the
zero
zero
It has
It
some
has some
corrosivity
corrosivity and
remnants
remnants
for zero
for
magnetic
zero
field
magnetic field
also. It
also.
is
It
not
is not
following the
following
same
the
path,
same path,
but in
but in
case of
case
super
of super
paramagnetism,
paramagnetism,
it is
it is
symmetric about
symmetric
the
about the
origin,
origin,
and it
and it
saturates
saturates
higher
higher
magnetic field,
magnetic field,
reaching a
reaching a
maximum value
maximum
of
value of
magnetization.
magnetization.
So no
So no
corrosivity, so
coercivity, so
H is
H
equal
is
to
equals to
zero.
zero.
No
No
remnant
remnant
magnetization, that is
magnetization, that
MR
is
equals
MR
to
equals to
zero,
zero,
and
and
magnetization is
magnetization is
returning to
returning
zero
to
when
zero
the
when the
external field
external
is
field
removed.
is removed.
So
So
the
the
sharpness.
sharpness,
Ma'am, what is coercivity?
So you
so
can
you can
see
see
this.
this.
Just a
Just a
second.
second.
So
So
you can
you can
define.
define.
Here we
Here
are
we are
having the
having the
MH plot,
MH
right?
plot, right?
Hello.
Hello.
Yes, ma'am.
Ah.
Ah,
So
so
so when
so
you
when
will
you will
remove the
remove the
magnetic
magnetic
field,
field,
so when
so remove the magnetic
remove
field means
demagnetization,
demagnetization.
so
So
it will tell
it
us
will tell
the
us
measure
the
of
measure
magnetic
of a
materials
magnetic material's
resistance.
resistance.
So when
So when
to be
to be
like
like
when
when
we
we
are
are
removing the
removing
magnetic
the
field,
magnetic field,
so
so
how much
how
magnetic
much
field.
magnetic
So
field.
suppose we
So
have
suppose
removed
we
the
have
magnetic
removed the
field,
magnetic field,
still there
still
is,
there is
we are not
we are
getting
not getting the SC is equals to zero. It means
how
how
much
much
magnetic
magnetic in
magnetic field
magnetic field in
that
opposite direction we need to
the
do
HC
the
is equal
HC
to
is
zero.
equals to zero.
That is
That
defined
is
as
defined as the
corrosivity.
corrosivity.
So it
So
is, I think
I
units
think
is
units
just
is just
amperes per
amperes
meter.
per meter.
So high
So high
corrosivity,
corrosive.
if I am
If
saying
I'm
that
saying that
this
this
material is high
material is high
corrosivity, it
corrosivity,
means
it
I need
means
a
I
very
need a very
strong reverse
strong reverse
magnetic field
magnetic field
to lose
to
its,
lose its
for a
for a
material to lose
material to
its
lose its
magnetism.
magnetism.
Is that
Is
clear?
that clear?
Yes, ma'am.
Okay.
So
So
then
then
the
the
sharpness,
sharpness.
yeah. So
Yeah. So
here we
here
were.
we were.
So
So
we were saying
we were
that
saying that
now
now
when the
when the
size is
size is
lesser than
lesser
the
than the
20
20
nanometer,
nanometer,
there are
there
no
are no
dominant
dominant
walls
walls
and the
and the
material is
material is
acting as a
acting as a
giant
giant
magnet.
magnet.
Next, we were
Next, we were
seeing the
seeing the
what is the
what is the
what is the
what is the
effect of the
effect of the
thermal
thermal
fluctuation.
fluctuation.
So here
So
we
here
are
we
showing
are
that
showing that
there are two
there are two
temperatures.
temperatures.
You can
You
see
can
T1
see
and
T1
T2.
and T2.
So at
So
higher
at higher
temperature,
temperature,
the spin
the spin
fluctuate more.
fluctuate more.
The spins
The spins
fluctuate more,
fluctuate
leading
more,
broader
leading
and
broader
shallow
and
curves.
shallow curves.
But at lower
But at lower
temperature, the
temperature, the
magnetic moments
magnetic
align
moments
more
align
easily,
more
leading
easily,
to the
leading to the
sharper curve.
sharper
So
curve.
it is
So it is
defined by
defined
the
by the
thermal
thermal
energy.
energy.
Then
Then
there are
there
some
are some
application of
application of
super
super
paramagnetism.
paramagnetism.
So
So
these
some
are the
these are the
natural,
natural these are the
naturally
naturally
occurring
occurring
super
super
paramagnetic
paramagnetic
substances in
substances in
tissues.
tissues.
And
And
other than
other than
that,
that,
uh,
um,
so the
so the
last
last
part of
part of
this
this
is,
is,
so
so
now
now
we
we
talked
talked
about the
about the
first is
first is
introduction to
introduction to
nanomaterial nanoparticles.
nanoparticles
Then
Then
second is
second is
classification.
classification.
Then
Then
is
is
needs,
needs,
and now
and
the
now the
applications.
applications.
So
So
first of
first of
all,
all,
why are
why
we
are we
interesting
interesting
in
in
the
the
nanomaterials?
nanomaterials?
So
So
the
the
ability of
ability of
materials to
materials to
dramatically
dramatically
change their
change their
properties at
properties at
nanoscale
nanoscale
has
has
opened up the
opened up the
possibility of
possibility of
making new
making new
devices,
devices,
instruments,
instruments,
and
and
consumer
consumer
goods.
goods.
So
So
we have
we have
seen that
seen that
like
like
energy
energy
consumption
consumption
is
is
lesser,
lesser,
and
and
automobiles,
automobiles, in
tires
tires
also we are
also we are
using the
using the
carbon
carbon
nanoparticles to
nanoparticles
give
to give
the
the
higher
higher
electrostatic
electrostatic
strength.
strength.
Also,
Also,
mm,
um,
energy
energy
storage
storage
like
like
supercapacitors.
supercapacitors.
So
So
how does
how does
nanotechnology
nanotechnology
is
is
helping
helping
to
to
increase the
increase the
supercapacitor
supercapacitor
energy
energy
density?
density?
So
So
I think
I
it's
think it's
there.
there.
Mm, okay, it will
Okay, it will
come
come,
first.
but
Okay,
okay.
then I will
And I'll
discuss at
discuss
that
at that
time
time
also.
also.
So if
So
you're
if you're
talking about
talking about
nanotechnology and
nanotechnology and
energy
energy
applications,
applications,
so
so
we are
we
using
are using
solar, wind,
solar, wind,
hydrogen,
hydrogen,
renewable sources,
renewable sources,
energy
energy
storage,
storage, batteries, and
batteries, and supercapacitors,
supercapacitors,
energy
energy
conservation,
conservation,
efficient
efficient
insulation, smart
insulation,
grids.
smart grids.
So
So
advantages are
advantages are
higher
higher
efficiency, faster
efficiency, faster
charging,
charging,
longer
longer
lifespan,
lifespan,
lower cost,
lower
and
cost, and
sustainability.
sustainability.
So
So
this
this
the next
the
is
next
more
is more
slow.
slow.
We have
We
already
have already
saw
saw
this.
this.
So
So
what is the
what is the
solution of
solution
that?
of
In
that?
spite
In
of
spite of
silicon, we are
silicon,
using
we are
the
using
carbon
the carbon
nanotubes,
nanomaterials, basically carbon
nanotubes,
nanotubes,
graphene,
graphene,
which will
which
offer
will
us
offer
the
us
higher
the higher
electron
electron
mobility,
mobility,
higher
higher
strength,
strength,
and
and
better
better
uh,
uh,
thermal
thermal
conductivity than
conductivity than
silicon.
silicon.
So it will
So it
be
will be
more
more
efficient
efficient
transistor.
transistors.
And in
And in
solar
solar
cells
cells
also.
also,
So
so
this is
this is
the
a
various
various
parts
parts like
ITO
ITO
coated
coated
glass,
glass,
electron
electron
transport
transport
layer,
layer,
absorber
absorber
layer,
layer,
hole
hole
transport. So
transport.
what
So
are we
what are we
using?
using?
So
So
in
in
each
each
part,
part,
the
the
nanomaterials
nanomaterials
uh,
uh,
are being
are being
used.
used.
So
So
for
so for
metal back
metal back
contact, we
contact,
are
we
using
are using
silver and
silver and
aluminum
aluminum
nanoparticles, and it
nanoparticles,
will
and it will
improve the
improve the
reflectivity.
reflect.
So since it
So
is
since it
metal,
is metal,
reflective
reflective
properties will be
properties
there,
will be there,
and
and
at
at nanoparticle
we
rate
have
we have
improved the
improved the
conductivity also.
conductivity also.
Then
Then
similarly, whole
similarly, whole
transport layer,
transport layer,
the
the
nanoparticles will
nanoparticles will
facilitate.
facilitate.
So
We
that the
saw that the
transportation
transportation, it will
help
have
in
help
the
in the
transportation,
transportation,
that is also
that is
there.
also there. Then
Electron
electron
transport layer,
transport layer,
TiO2
TiO2
nanoparticles,
nanoparticles,
nanorods are
nanorods
there.
are there.
So
So
we are
we are
using
using
nanoparticles
nanoparticles
in the
in the
solar
solar
cells,
cells, which
so that
so that
through
through
nanotechnology we are
nanotechnology we are
moving from
moving from
sustainable
sustainable
development.
development.
Then
Then
nanotechnology in
nanotechnology in
batteries.
batteries.
So
So
here
here
in
in
major
major
parts
parts
of the
of the
battery where
battery where
nanomaterials we can
nanomaterials we
use
can
as
use as
anode and
anode and
cathode
cathode
materials,
materials. There are various
materials
materials
which
which
will
will
increase
increase
the
the
surface
surface
area,
area
that will
that will
provide us
provide
the
us the
higher
higher
energy
energy
storage
storage
capacity,
capacity,
better
better
mechanical
mechanical
flexibility,
flexibility,
and
and
since
since
shorter
shorter
diffusion
diffusion
paths, it
path, so
will
it will
increase the
increase the
faster
faster
charging and
charging and
discharging.
discharging.
So, so now
So now
we'll see
we'll
that
see
how the
that how the
nanotechnology is
nanotechnology is
helping the
helping the
fuel cells.
fuel cells.
So
So
since
since
high surface
high
area,
surface
faster
area,
charging,
faster
tunable
charging, tunable
properties,
properties,
and
and better
durability.
durability.
So
So
I can,
I can,
yeah.
yeah.
So we know
So
that
we
the
know that the
capacitance is
capacitance
defined
is
by
defined by
C is equals
C
to
is
Q
equals
by
to
D,
Q
that
by
is
D, that is
epsilon
epsilon
A
naught
by
K
D,
A
where
by
A
D,
is
where
the
A is
surface
the
area of
surface
the
area of the
electrode,
electrode,
and D is
and the
the
D is
distance
the
between
distance between
two
two
electrode. So
electrode.
how can
So
we
how can we
increase the
increase the
capacity?
capacity?
Either by
Either by
increasing A
increasing A
or by
or by
decreasing D.
decreasing D.
So
So
this is the
this is the
conventional
conventional
capacitor,
capacitor
where
where
we have
we
this
have this
dielectric,
dielectric
metal
metal
electrode, cathode
electrode,
and
cathode and
anode,
anode, and
this is the
This is the
area,
area,
and this
and
is
this is
the
the
distance
distance
between these
between
two
these two
plates.
plates.
So
So
now,
now,
when we are
when we are
dealing with
dealing
the
with the
electrochemical
electrochemical
double layer
double layer
capacitor, what
capacitor,
is
what is
happening
happening
here?
here?
We are
We are
we are
we are
using the
using the
porous
porous
substrate.
substrate.
So
So
because of
because of
that
that
porous,
porous,
it will
it
give
will give
a
a
higher
higher
surface
surface
area,
area,
so
so
that
that
A will
A will
increase,
increase,
and
and
that
that
will
will
increase the
increase the
electrostatic
electrostatic
ion
ion
adsorption,
adsorption,
so
so
which will
which will
allow us
allow
to
us to
rapid
rapid
charging
charging and
discharge
discharge
cycles in
cycles
seconds
in
with
seconds
higher
with
energy
higher energy
density.
density.
So
So
because of
because of
using
using
nanomaterials, we
nanomaterials,
can
we can
increase the
increase the
storage powers
storage
in
powers in
supercapacitor.
supercapacitor.
Then again,
Then again,
there is a
there is a
role in
role
medicine.
in medicine.
So in
So in
medicine,
medicine,
nanomaterials have
nanomaterials
opened up.
have opened up.
Obviously, we can do
Obviously, we can do
endoscopy.
endoscopy.
We can
We can
we are doing
we are doing
MRI.
MRI,
MRI.
MRI.
We can
We
see
can
the
see the
tomographical
tomographical
properties of
properties
the
of the
particles.
particles.
Antibacterial
Antibacterial
infection we can
infection we
remove.
can remove.
So
So
even in
even in
anti-diabetic
anti-diabetic
therapy,
therapy,
people are using
people are
this
using this
nanoparticles.
nanoparticles.
So
So
so that we can
so that we can
early
early
diagnosis and
diagnosis and
do the
do
imaging
the
using
imaging using
MRI. Obviously,
MRI. Obviously,
antibacterial and
antibacterial and
antiviral
antiviral
application.
application.
We can do the
We can do the
targeted
targeted
drug
drug
delivery.
delivery.
So these are
So
all
these are
things we
all
have
things we have
already
already
mm, covered
covered.
in
In
domestic
domestic
application. So
application,
now we
so
are
now we are
using
using
this
this
washing
washing
machine
machine
nano
nano
silver
silver
technology
technology
is
is
using to
using to
disinfect
disinfect
cloths and
cloths and
water.
water.
Carbon
Carbon
nanotubes and
nanotubes and
nano
nano
ceramic
ceramic
filters we are
filters we are
using to
using
remove
to remove
contaminants and
contaminants and
bacteria.
bacteria.
And for
And for
personal
personal
cosmetics,
cosmetics,
beauty
beauty
products,
products,
sunscreens, we are
sunscreens, we are
using
using
nanoparticles.
nanoparticles.
Defense and
Defense and
applications
applications
also.
also,
Uh,
uh,
since it is
since it is
lightweight, we are
lightweight,
using
we are
this.
using this.
And
And
high
high
mechanical strength
mechanical
in
strength
radars
in
also
radars
we are
also
using.
we are using.
So there are
So
various
there are
using
various
carbon.
using carbon.
So
So
since
since
carbon
carbon
nanotubes,
nanotubes,
graphene
graphene
nanocomposites
nanocomposites
are
are
of the
of the
lighter weight
lighter
and
weight
better
and
fuel
better fuel
efficiency, we are
efficiency, we
using
are
this.
using this.
Also,
Also,
fuel
fuel
economy
economy
we are
we are
decreasing by this.
decreasing by this.
And
And
since it is
since
because
it is
of
because of
durability,
durability,
performance, and
performance, and
flexibility of
flexibility of
2D
the
materials,
2D
we are
materials,
using
we are
it.
using it.
And high
And
strength
high
also,
strength
we are
also,
using
we are
bike
using
skills,
bike
golf
skills golf
materials.
materials.
So we are
So
using
we are
in
using
our day
in
to
our
day,
day to day,
textile
like textile
industries also, in
industries also,
fabrics
in
also,
fabrics also,
we are using
we are
this
using this
for
for and
bacterial,
bacterial,
antibacterial,
antibacterial,
antimicrobial
antimicrobial
applications
activities
also.
also.
So more or
So
less,
more or less,
so
so
what is
what is
the
the
concluding
concluding
final
final
concluding
concluding
message
message
from this whole
from this whole
lecture?
lecture?
That
That
nanomaterials
nanomaterials
representing
representing
us a
us a
distinct
distinct
phase of
phase of
matter
matter,
which is
which is
governed by
governed by
high
high
surface free
surface free
energy,
energy,
quantum
quantum
mechanics,
mechanics,
and we
and we
have
have
infinite
infinite
potential
potential
to
to
engineer
engineer
technology
technology
at the
at the
atomic
atomic
level.
level.
So,
So,
basic
basic
difference
difference:
in a
in a
bulk
bulk
material,
material,
we
we
deal with
deal
the
with the
physical
physical
properties like
properties like
density,
density,
melting
melting
point,
point,
electrical
electrical
conductivity.
conductivity,
That
that
remain
remain
constant
constant
if we are
if we are
changing,
changing,
regardless of
regardless
the
of the
size.
size.
But in a
But in a
nanomaterial,
nanomaterial,
physical
physical
properties
properties
become
become
size
size
dependent. We
dependent.
can
We can
tune that
tune that
depend
depend
due to
due
the
to the
dominant
dominant
surface
surface
energy and
energy
the
and the
quantum
quantum
mechanical
mechanical
confinement
confinement
effects.
effects.
So
So
I have
I have
discussed
discussed
about
about
surface
surface
area
area
increases
increases
because of
because of
surface
surface
area to
area to
volume
volume
ratio, that
ratio,
is
that is
3 by
3 by
r.
r.
And
And
then we
then we
discuss
discuss
about the
about the
quantum
quantum
dot, that
dot, that
is
is
a
a
zero
zero
dimensional
dimensional
semiconductor,
semiconductor,
where
where
because the
because the
dimensions
dimensions
are in
are in
the
the
all the
all the
three
three
directions,
directions,
and that
and
will
that will
form
form
the
the
atomic like
atomic like
energy
energy
levels,
levels,
and
and
it will
it
give us the
will give
size
us the size
dependent
dependent
uh,
uh,
photoluminescence.
photoluminescence.
So
So
now,
now,
just
just
want to
want to
explain
explain
one more
one
time
more
the
time the
LS. What
LS,
is
what is
LSPR
LSPR
in gold
in gold
nanoparticles,
nanoparticles,
and
and
why it
why
is
it is
depending
depending
upon the
upon the
dielectric
dielectric
constant
constant
also.
also.
So when
So when
LSPR, when
LSPR,
it
when
will
it will
happen, when
happen, when
light will
light will
interact with the
interact with the
conduction
conduction
electrons in
electrons in
metallic
metallic
nanoparticles,
nanoparticles,
it will
it will
create the
create the
coherent
coherent
dipole
dipole
oscillation.
oscillation.
So when
So
the
when the
resonant
resonant
condition
condition
is
is
met,
met,
that
that
is
is
epsilon
epsilon m
omega
omega
is
is
equals to
equals to
minus 2
minus 2
epsilon
epsilon
d,
d,
where
where the
epsilon m
epsilon
is the
m is the
metallic
metallic
dielectric
dielectric
function and
function and
epsilon d
epsilon
is the
d is the
surrounding
surrounding
medium.
medium.
So
So
wherever there
wherever
is
there is
any
any
change in the
change in the
local
local
refractive
refractive
index,
index,
it
it
will
will
shift the
shift the
plasmon
plasmon
wavelength
wavelength
that
that
will
will
enable
enable
the
the
optical
optical
biosensing.
biosensing.
So
So
that's why
that's why
because of
because of
that
that
phenomena
phenomena
only,
only
uh,
uh,
it is
it is
very
very
helpful in
helpful in
biosensors.
biosensors.
And
And
so
so we
we
studied
studied
about
about
weak
weak
and
and strong
strong
quantum
quantum
confinement
confinement
resins.
resins.
So
So
when
when
the
the
particle
particle
size
size
is
is
greater than
greater
the
than the
Bohr
Bohr
exciton
exciton
radius
radius
but
but
smaller than
smaller
the
than the
bulk
bulk
dimension,
dimension,
what will
what
happen?
will
The
happen?
Coulomb
The Coulomb
interaction between the
interaction between
electron
the
and hole
electron
will
and hole will
dominate, and
dominate, and
confinement will
confinement
act as a
will
small
act as a small
perturbation.
perturbation.
And
And
when we will
when
be
we
in
will
a
be in
strong
the strong
confinement region,
confinement region,
when particle
when
size is
particle size is
significantly
significantly
smaller
smaller
than the
than
both
the
electron
both
and
electron
hole
and
both
hole both
radii,
radii, Bohr
and
radii,
the
and the
individual
individual
kinetic
kinetic
energy
energy
is proportional
is
to 1 by
proportional to
r
1 by
square
r
that will
square that will
dominate of
dominate
over the
of over
Coulomb
the Coulomb
interaction.
interaction.
So it will
So it
decouple
will
the
decouple the
whole
electron whole
wavelength
wavelength
into
into
independent
independent
quantiles
quantiles
states.
states.
So
So
now
now
uh,
uh,
this was
this was
all about
all about
the
the
lecture.
lecture.
Like
Like
first we
first
discuss
we
about the
discuss about the
nanomaterials
nanomaterials
introduction. After
introduction.
that we
After
discuss
that, we
about the
discuss about the
classification, then the
classification, then the
need, and
need,
then the
and then the
application.
application.
So now
So now
it's very
it's very
easy
easy
module
module
that
that
was
was
uploaded.
uploaded.
Um, yeah.
Yeah.
So what
So what
property will
property will
increase as the
increase as the
particle size
particle size
decreases in
decreases in
nanomaterials? So one
nanomaterials?
is
So one is
density,
density,
mass,
mass,
melting point,
melting
or
point,
surface
or
to volume
surface to
ratio. So
volume
we
ratio. So
saw
we
that
saw that
the
the
surface to
surface
volume
to
ratio
volume
is
ratio is
changing,
changing,
is
is
increasing
increasing
when
when
the
the
particle size
particle
is
size is
decreasing.
decreasing.
So
So
the answer
the
is
answer is
surface to
surface
volume
to
ratio.
volume ratio.
The second
The
is
second is
which
which
ancient
ancient
artifacts
artifacts
exhibit color
exhibit
change
color
due to
change due to
nanoparticle
nanoparticle
effects.
effects.
So
So
in the
in
slides
the
also it
slides
was
also it was
mentioned
mentioned
that
that
like a
like
whisk
a
cup
whisk cup
is that
is that
because it
because
is
it
made
is
up of
made up of
nanoparticles. That's
nanoparticles.
why
That's why
Mona Lisa
Mona Lisa
painting is
painting
not
is
made
not
of
made
that
of that
nanoparticle. If
nanoparticles.
it
If
was
it
made
was
of
made of
nanoparticles,
nanoparticles,
it
it
could
could
exhibit the
exhibit the
same
same
effect. But
effect. But
this
this
cup
cup
is made
is
up of
made up of
the
the
size
size
lesser than
lesser than
the
the
range of
range
10
of
to
10 to
100
100
nanometer. That's
nanometer.
why it
That's why
is
it is
showing the
showing the
color
color
change due to
change due to
nanoparticle
nanoparticle
effects.
effects.
Why don't
Why
we
don't we
use
use
peak over
pico or
femtosite
femtosite
materials
materials
practically?
practically?
Can
Can
anyone?
anyone tell?
Okay,
Okay,
so
so
we
we
talk
talk
about
about
when
when we are
moving
moving
from
from
beyond
beyond
nanoparticle
nanoparticle
to
to
peak or
peak or
femto.
femto.
The
The
instability
instability
in,
in,
first of
first of
all,
all,
we
we
can't
can't
manipulate.
manipulate.
So
So
on the
on the
technology
technology
available,
available,
and
and
then
then
we are
we are
moving
moving
from the
from the
subatomic
subatomic
level, that
level,
is
that is
proton
proton
electrons. So
electrons.
at
So at
that
that
we
we
have
have
no
no
control
control
over the
over the
structures.
structures.
So
So
no
no
stable
stable
structure is
structure is
possible.
possible.
If the
If the
stability
stability
is not
is not
there,
there,
how can
how
we
can we
perform
perform
and how
and
can
how
we
can we
find the
find the
applications of
applications of
these
these
materials? Because
materials? Because
depending
depending
upon the
upon the
structures,
structures,
size,
size,
we are
we are
choosing the
choosing the
applications.
applications.
Now,
Now,
surface to
surface to
volume
volume
ratio of a
ratio of a
spherical
spherical
particle is
particle is
proportional
proportional
to,
to.
so we
So
saw
we
that
saw
4
that
by
4
3
by
pi
3
r
pi r
cube
cube
upon
upon
4 pi
4
r
pi r
square
square
upon 4
upon
by
4
3
by
pi
3
r
pi r
cube.
cube.
So
So
it
one,
was
it was
proportional to
proportional
3
to
by
3
r.
by
So
r. So
3 is
3 is
constant, so
constant,
1
so
by
1
r.
by r.
So
So
surface to
surface to
volume
volume
ratio of a
ratio of a
particle is
particle is
proportional to
proportional
1
to
by
1
r.
by r.
Then which
Then which
microscopy
microscopy
technique is
technique is
commonly
commonly
used to
used
view
to view
nanoparticles? So
nanoparticles?
first
So
is
first is
optical
optical
microscope.
microscope.
So
So
it has
it
world
has word
microscope. So
microscope. So
and the
and the
particle size
particle
is
size is
nano. You
nano.
can't
You can't
see
see
nanoparticle size in
nanoparticle size in
optical
optical
microscope.
microscope.
Then
Then
XRD,
XRD,
it
it
is,
is,
and
and
TG
TG
both are
both are
used
used
to
to
see the
see the
what is
what
the
is the
composition of the
composition of the
material, like
material, like
elemental
elemental
analysis we
analysis
can
we
do
can do
using
using
these
these
techniques.
techniques.
We can
We
tell
can tell
what types
what
of
types of
material are
material are
present, but we
present, but we
can't
can't
see
see
the,
the
but we
but
can't
we
view
can't view
the
the
particle
particle
size of
size of
nanoparticles.
nanoparticles.
So
So
using
using
SCM
SCM
technique,
technique,
where the
where the
electrons are
electrons are
bombarded,
bombarded
using
using
scanning
scanning
electron
electron
microscopy
microscopy
only, we
only,
can
we
see
can
the
see the
nanoparticles.
nanoparticles.
Now,
Now,
engineered
engineered
nanoparticles
nanoparticles
are
are
characterized by.
characterized by.
So we saw
So we
that
saw that
there were
there were
incidental
incidental
nanoparticles.
nanoparticles.
There are
There
various
are various
characterization like
characterization like
natural,
natural,
incidental. In
incidental. In
incidental
incidental
part,
part,
engineered
engineered
nanoparticles
nanoparticles
was a
was a
subpart of that.
subpart of that.
So
So
engineered
engineered
nanoparticles,
nanoparticles,
under which
under which
category? It is the
category? It is the
category of the
category under
intentional design.
intentional
Because
design. Because
whatever
whatever we
like
like
we have
we have
lithography
lithography
techniques
techniques
according to
according
the
to the
structure, we
structure,
can
we can
engineer our
engineer our
nanomaterials. So it
nanomaterials. So
was
it
under
was
the
under the
category
category
intentional
intentional
design.
design.
Which
Which
dimension?
dimension?
Which
Which
dimension
dimension
class has
class has
all the
all
three
the three
dimensions
dimensions
lesser than
lesser than
100
100
nanometer?
nanometer?
So
So
zero
zero
dimension.
dimension,
Uh,
uh,
for the
for
zero
the zero
dimensional
dimensional
materials,
materials,
all the
all
three
the three
dimensions were
dimensions were
lesser than
lesser than
100
100
nanometers.
nanometers.
In
In
1D,
1D,
it
it
was in
was
the
in the
only in
only
one
in one
dimension.
dimension.
In the
In
two
the two
dimension, the
dimension,
size
the
was
size was
lesser than
lesser than
100
100
nanometer, but
nanometer,
in
but
one
in one
dimension, it
dimension, it
was
was
greater than
greater than 100
nanometer. So the
nanometers. So the
correct
correct
answer is
answer is
option D,
option D,
where we
where
have
we
all
have
the
all
three
the three
dimensions
dimensions
lesser than
lesser than
100
100
nanometer.
nanometer.
Then what is
Then
the
what is the
key
key
feature of
feature of
1D
1D
nanomaterials?
nanomaterials?
So
So
first is
first is
isotropic
isotropic
behavior.
behavior.
So
So
what
what
were
were
1D
1D
nanomaterials?
nanomaterials?
In the
In
two
the two
direction,
direction,
the
the
size of
size of the
the
particle
particle
size
size
is
is lesser than
lesser than
100
100
nanometer.
nanometer.
In one
In one
direction, the
direction, the
particle
particle
size
size
is
is
greater than
greater than
100
100
nanometer.
nanometer.
So
So
when the
when the
size
size
particle is
particle is
greater
greater
than
than
100
100
nanometer,
nanometer,
obviously
obviously
the
the
properties
properties
will
will
change
change
in one
in one
direction.
direction.
Because of
Because of
that,
that,
it is
it is
no
no
longer
longer
isotropic.
isotropic.
Then it
Then
will
it will
start
start
showing you
showing you
an
an
isotropic
isotropic
property.
property.
So
So
1D
1D
nanomaterials will
nanomaterials will
feature
feature
an
an
isotropic
isotropic
property. So the
property. So the
correct
correct
answer
answer
is
is C.
then what
Then
is an
what is an
example of a
example of a
2D
2D
nanomaterial?
nanomaterial?
So we
So
saw
we
that
saw that
0D
0D
quantum dot
quantum
is a
dot is a
0D,
0D,
nano
nanorod
nanorod is
nanorod
a
is a
2D
2D
material,
material,
uh, a
a
2D
2D
nanomaterial,
nanomaterial,
and
and
dendrimer was
dendrimer
a
was a
chain of
chain of
uh,
uh,
nanorod is a
nanorod is a
1D,
1D,
then
then
dendrimer is
dendrimer is
a chain
chain
polymer
polymer
molecules, and
molecules, and
graphene is a
graphene is
2D
a 2D
material.
material.
Then
Then
how can
how
we
can we
define the
define the
dendrimers?
dendrimers? We
Have
have
we have
we have
discussed all
discussed
these
all these
questions.
questions.
So
So
that's why
that's
I'm
why I'm
going
going
very
very
fast.
fast.
Dendrimers are
Dendrimers are
defined as
defined as
branched
branched
polymeric
polymeric
molecules
molecules
because we
because
saw
we
that
saw that
dendron is
dendron is
free
free
and it
and
has
it
a
has a
chain
chain
molecules.
molecules.
So
So
branched
branched
polymeric
polymeric
molecules is the
molecules, the
correct
correct
answer.
answer.
Why do
Why do
nanoparticles have
nanoparticles
high
have high
reactivity?
reactivity?
So
So
when we are
when we are
moving
moving
from
from
bulk to
bulk to
nanoparticles,
nanoparticles,
the
the
surface
surface
area was
area was
increasing. So we
increasing. So
have
we have
high
high
surface
surface
area.
area.
That's why
That's
we
why we
have
have
more
more
number of
number of
unfulfilled
unfulfilled
bonds
bonds,
so
so
that
that
they
they
can
can
create the
create the
dangling
dangling
bonds.
bonds.
That's why
That's
the
why the
reactivity is
reactivity is
higher. So
higher.
we,
So
since we
we
have the
have the
high
high
surface
surface
area in
area in
nanoparticles,
nanoparticles,
we have
we have
high
high
reactivity. So the
reactivity. So the
correct
correct
answer is
answer
high
is high
surface area.
surface area.
Then
Then
uh,
uh,
which
which
property
property
improves due
improves
to
due
Hall
to Hall
patch
patch
effect?
effect?
So we
So
saw
we
that
saw that
what we
what
see
we see,
what was
what
the
was
Hall
the Hall
patch
patch
effect
effect
uh,
uh,
telling
telling
us
us
regarding the
regarding the
grain
grain
boundaries.
boundaries
And
and
what was
what was
grain
grain
boundary doing?
boundary doing.
So when
So
the
when the
grain
grain
nanoparticle,
nanoparticle,
the
the
grain
grain
boundary
boundary
will
was
increase, and
increased, and
hence the
hence the
dislocation
dislocation
will
will
enhance.
enhance.
So
So
because of
because of
that,
that,
the
the
mechanical
mechanical
strength will
strength will
increase.
increase.
So the
So
whole
the Hall
patch
patch
effect is
effect is
related to
related
the
to the
mechanical
mechanical
strength.
strength.
Super
Super
paramagnetism
paramagnetism
is
is
observed in
observed in
particles
particles
typical
typical
below. So
below.
you
So you
can
can
see
see
we are
we are
dealing with
dealing with the
nanoparticles where
nanoparticles
we
where
are
we are
showing
showing
the
the
super
super
paramagnetism
paramagnetism
can
can
occur.
occur.
So
So
it
it
should be in
should be
this
in this
size of
size of
less than
lesser than
100
100
nanometer.
nanometer.
So
So
obviously there
obviously
is
there
only
is
one
only one
option which is
option which is
showing the
showing the
nanoparticle
nanoparticle
size which
size
is
which
less
is
than
lesser than
100
100
nanometer.
nanometer.
So
So
super
super
paramagnetism
paramagnetism
can be
can be
observed
observed
in
in
particles
particles
typical below
typical below
100
100
nanometer.
nanometer.
then
Then
what
what
is
is
the
the
shape
shape
of
of
MH
MH
curve
curve
in
in
super
super
paramagnetism? So
paramagnetism?
that
So
it
that it
is
is
S
S
shape
shape
symmetric
symmetric
about the
about the
origin,
origin,
that is
that
called
is called
sigmoidal
sigmoidal
shape.
shape.
And
And
last
last
question is
question is
localize the
localize the
phase
phase
plasmon
plasmon
resonance
resonance
occurs
occurs
due
due
to
to
collective
collective
electron
electron
oscillation. We
oscillation.
saw
We
that
saw that
collective
collective
electron
electron
oscillation,
oscillation,
which
which
electrons? Electrons in the
electrons in the
conduction
conduction
path.
path.
Okay,
Okay,
okay.
okay.
So
So
this is
this
all
is
about
all
the
about the
today's
today's
lecture.
lecture.
In the
In the
next
next
lecture,
lecture,
I will
I
try
will
to
try
show
to
you
show you
some more
more
STEM
STEM
images of
images
the
of the
waveguides
waveguides
and
and
resonators,
resonators,
which we
which
are
we are
fabricating in
fabricating
our
in our
labs or
labs or
NIT
NIT
using the
using the
central
central
facility,
facility,
so that
so
you
that you
guys can
guys
have
can have
idea,
idea
like
like on
if we are
if we are
dealing with
dealing with
the
the
nanometer
nanometer
size,
size,
which
which
instrument should we
instrument should we
use.
use.
Then
Then
if we are
if we are
dealing with
dealing with
the
the
micro
micro
lasers,
lasers,
then what
then what
instrument should we
instrument should we
use.
use.
So
So
I will
I
give
will
you
give
a
you a
thorough
thorough
idea
idea
about all
about
these
all
things,
these things,
and the
and the
principal and
principle and
working
working
area
area
we will
we will
discuss in
discuss
the
in the
upcoming
upcoming
weeks.
weeks.
So
So
this is
this
all
is all
about
about
today's
today
lecture.
lecture.
So
So
if there
if
is
there
any
is any
doubt you
doubt,
can
you
ask,
can ask.
otherwise
Otherwise,
we can
we can
conclude this
conclude this
session.
session.
Ma'am, please discuss the assignment questions,
So
which
So
is
that
currently.
so
so
that we
that we
can
can
discuss
discuss
when the
when the
deadline
deadline
will be
will be
done.
done.
So
So
you
you
guys have
guys have
deadline for
deadline
that,
for that,
right?
right?
Yes, ma'am.
Yes.
Yes.
So we
So
are
we are
not
not
supposed to do
supposed to do
that.
that.
After the
After the
deadline
deadline
only we
only
can
we
tell
can
the
tell the
correct
correct
answers.
answers.
Okay,
Okay,
so
so
no other
no other
doubt.
doubt.
So
So
I'm
I'm
canceling this
canceling
with.
this with.
Okay.
Okay.
Ma'am,
Huh?
Huh?
ma'am, how can I get your PPT sheet, ma'am?
I will
I will
upload it.
upload
I
it.
will
I will
upload it.
upload it.
Thank you, ma'am.
Okay.
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 Thank you
Thank
all.
you all.
Thank you, ma'am.